My name is Pablo. Hi.
Good morning in the room. Good morning, everybody. We are about to start up our final leg of the conference, the final day. Wow, yesterday was really a good social, wasn't it? Some of you look a little bit more tired than when I saw you last time, but I guess that's to be expected. We have a day of program today. We have a number of speaks here in the morning. We have one coffee break and a lunch break. There's a couple of details I want to mention. The surveys for this day's program will come up shortly. There will be also a general survey for the conference as well. That will also be available, hopefully, later today as well. We still have a lot of t-shirts left. We will make sure that you can get your t-shirts maybe in the first coffee break, otherwise during the lunch break. So if you haven't got your t-shirt yet, there will be opportunity for you to get it. I'm supposed to fill up 10 minutes now, or 20. I'm not able to do that, so I think we'll start the program a little bit early today, and then we can enjoy a little bit longer break towards the coffee break. It is my big pleasure to invite to the stage Pablo from Cisco that will talk about segment routing SRv6. So please give him a warm welcome.
Hi, good morning, everyone. How are you? Many thanks for your time and for joining. So this is SRv6. I would like to give you an update on the technology and the deployment status. Here. So first is really to start with a double thank you. So it's really a thank you to the lead operators, thank you to the ecosystem partners, to the academic partners, IETF, and the Cisco segment routing team, because this year is actually the 10th anniversary of the segment routing project. Segment routing started when a Cisco colleague, he was driving actually from Rome to Brussels. And along the journey, there is one tunnel, that is the tunnel of Gotardo, that is often congested. And so the question is, well, what do I do if this tunnel is congested? So what do I do if this tunnel is congested? And this started the realization that as human beings, when we need to reroute, we don't send a guy in a horse with a sign that has to identify me and my car and is telling me turn left or turn right. So that is SVVT. No, instead we take a way simpler approach that is just simply to say, well, go to the shortest path to Chamonix, take the Mont Blanc tunnel, and then take the shortest path to Rome. And so this kicked the idea that we can do way simpler things in networking, and we can really simplify and make something that is leaner and more scalable. So really, over these last 10 years, we have achieved fantastic things with segment routing. Today, I only have 30 minutes to give this presentation, and so as always, we maintain the segmentrouting.net website. As I only have 30 minutes, I will give you a bit the highlights. I will explain you what is the new things. However, all of the detailed information, because I won't have time to cover it, you have it here. So you have the pointers in the slides, the links. And so you will have very detailed trainings, demos, etc. So deployment status. SRv6 is really achieving record deployment status, the same as with SRMPLS. We only had 3 years of commercial deployment, so we started in 2019 with SoftBank. And already today we have over 100 million subscribers whose services are supported with SRv6. We have over 100 deployments, 14 of them with public reports across the web, service provider, and enterprise, and across different geographies, so in Asia, Europe, and America. Here you have the list of a few of the operators who have publicly announced their deployments. The new ones are in blue, and to highlight a bit that I will speak about later, Rakuten, Alibaba, and Bell Canada. So really, we are really happy to announce that in the past 3 months, Alibaba has deployed a full stack SRv6 network. From the application socket up to the peering link, full stack SRv6. It has been a great collaboration with the colleagues from Alibaba, with Joan Chow, Dennis, and Roy. And really here, the one of the key things is that this deployment, it has not only been done just with Cisco ISXR routers, but also they have leveraged, for example, white box devices with Sonic. They have also leveraged the SRv6 support in Kubernetes. So really, beyond the use case, it has been a very, very interesting journey. We have a very strong commitment to lead operators to deliver standard-based technology, to have a vendor ecosystem, very rich vendor ecosystem, to also deliver a very rich open source ecosystem, and I think this is achieved. We already had 3 proposed standard RFCs, so RFC 8402 on the segment routing architecture, RFC 8754 defining the SRv6 data plane, so the segment routing header, and RFC 8986, so the SRv6 network programming. Throughout the past few months, we have added 4 additional proposed standard RFCs covering the ISIS, BGP, OAM, and the segment routing policy. So really, this is a way faster speed of standardization than norm at IETF, and this is really a sign of the industry endorsement towards the SRv6 solution. We have a very rich ecosystem, not only from a vendor point of view, but also from an open source point of view. You have all of the details there. And we also had many successful interops, either at the NTC, at the Japan events like the ShowNet or the Net1, or NANOG. So the first technology that I would like to describe about is the stateless and scalable network partitioning for 5G slices. So the first process whenever this router R1 is receiving a packet is really to do a lookup on the destination address to determine which is the egress outgoing interface that is shown here in green. Now, if I want to partition my network, if I want to build partition for 5G slices, then what I will need to do is something very simple. With this technology, what we need to do is only to look into the partition ID, which is going to be a new field within the first 40 bytes of IPv6 header at a fixed offset. And I'm just going to select into which partition I need to schedule this packet. And then on top of that, obviously, I need to do a lookup on the DHCP to determine into which particular queue I'm going to put this packet into. So this is a very simple solution for doing the network partitioning. It is completely stateless. The destination address, the partition ID, and the DHCP, there are 3 fields that are within the first 40 bytes of the IPv6 header, so it's extremely easy for the hardware at a fixed offset. So there is no state, there is no classification, there is no DPI. It's just very simple for the hardware. This solution is also very scalable because actually these 3 fields, the destination address, the partition, and the DHCP, are actually orthogonal spaces. They are the routing, the partitioning, or the slicing, and the QoS. And this is a bit to compare with other proposals that are around at the IETF, where they are merging a bit the routing with the partitioning, and so it does not scale. So very simple solution. You have actually the demo link there. You can watch it, and quite straightforward. So then the core of my presentation, it will be around microSIDs. So microSIDs from an industry point of view, sometimes we call it SRv6 microSID, we call it SRv6 USID, or USID microSID, and at the IETF it is being standardized as the next CSID. So, well, for microSID, we are really, really happy to announce that Rakuten has actually deployed SRv6 microSID in their network. You have all of the details there, but Rakuten has deployed SRv6 for their 5G end-to-end network slicing network. They have 2 slices in their network, one for low cost, another one for low delay. They are delivering the VPN services, L3 VPN and L2 VPN services with SRv6. And on top of that, they have all of their fast route, so 50 millisecond fast route technology with the LFA. In addition, with Rakuten, we have done a great innovation with this, for example, the BGP peak core and edge with SRv6 summarization, that is the UPA. And we've also done a lot of innovation for the segment routing bandwidth counters for the capacity planning. A second deployment which has been very interesting is Bell Canada. So Bell Canada is really interesting because they were one of the first operators that deployed SRMPLS 5 years ago. And they have very quickly transitioned from SRMPLS to SRv6 microSID. The reason for them to do this transition is because with microSID, they were getting better routing scale for the summarization, and they were also getting better hardware scale from the hardware point of view. They also wanted to have an end-to-end unified IP data plane from the application socket up to the peering link. And on top of this, they deliver what they call service programming, which in the industry is commonly referred to as service chaining, which led to a fantastic cost in the reduction of significant reduction of the cost for belt canal services. And this has been done together with Noviflow, the service chaining appliances. So very interesting use case. At Cisco, we already have feature parity between SRv6 microSID and segment routing MPLS since June 2021. That is why you're already starting to see deployment reports on SRv6 microSID. So we already have the support for TLFA and the macro loop avoidance. We have support for the flex algo to do the slicing, the low cost and the low delay with the automated steering. We have the traffic engineering policy with either both topological or service SIDs. We have any sort of service, layer 3, layer 2, or internet transport, the VPN gateway. And last but not least, we also have the IP summarization, which is going to be great because it means that you no longer need to support BGP 3107 to carry your host routes. We have a very rich ecosystem. You have all of the list of logo there. We had an excellent collaboration in between all of the different partners, and not only from a vendor point of view, but also very importantly from the open source point of view, which is quite impressive. So what is microSID? microSID is a bit the continuation of the segment routing journey. And what was segment routing when we started? Well, segment routing, it's about going back to the root, to go back to the root of IP, to go back to the root of SIS, to go back to the root of BGP, and try to remove things which are needed, like, for example, LDP and RSVPD, that we removed them, and it was great. And so now with SRv6 microSID, what we are doing is we are continuing on that journey. We are going one step further. And so with microSID, what we are going to do is simply going back to the purity of IP, and the purity of IP is classless routing based on a subnet. And from a data plane point of view, this is just the longest prefix match that all of you know. So what is the benefit of building a solution on top of the longest prefix match? Well, first, that this is going to be straightforward to implement, piece of cake. And you saw the ecosystem before. We don't get such an ecosystem just by adding new functionalities. No, we get that ecosystem by really going back into the router, looking at the components, looking at the building blocks, and try to do things efficiently. And so, for example, just by leveraging these longest prefix match, what we get is things such as, for example, that we are able to support different sizes of microSIDs that can be combined together in the same SID list. Or, for example, we can process multiple microSIDs all at once in one single LPM look. And so just to take 1 minute and to compare it with MPLS. In MPLS, all of the labels have the same size. There is no flexibility. And in MPLS, if you want to process 2 labels, you actually need to circulate a packet, and this sometimes has a performance impact. So this is not an issue in microSID because we have the longest prefix match. So to illustrate a bit the benefit, one very simple example. If I have a PE device. On this PE device, I might have L3 VPN services. And these L3 VPN services, we know that at most I will have a few thousands of berths. So it seems quite efficient to allocate the seats, to allocate the services, using 16-bit IDs. On the other hand, if I have layer 2 VPN pseudo wires, for example, here I will have hundreds of thousands of different entries. And so 16-bit is not going to be enough. And for the L2 VPN services, it's more interesting to allocate them using 32-bit identifiers. So really, with the longest prefix match, what I'm getting is this flexibility to mix and match and being able to merge them. Now, SRv6 microSID was invented in 2016, like one of the first building blocks of SRv6. So it's actually fitting very well within the segment routing header, so the proposed standard RFC 8754. And it completely applies to the SRv6 network programming, so RFC 8986, because any microSID can be bound to any network programming instruction. Now, SRv6 microSID is offering the best SRv6 compression. So what you have on this graph on the x-axis is actually the number of transport segments, okay? So the number of seats that you will use for doing your traffic engineering policy. And on the y-axis, what you have is the encapsulation overhead, so the MTU overhead that you are putting into the packet. If I look, for example, at 10, so at 10 intermediate segments for traffic engineering, with SRv6, the overhead is 208 bytes. With SRv6 microSID, you are going down to 64 bytes. So really, it's 3 times less. So quite significant. And we are the best with the microSID compression, and this is a bit to compare it with other proposal that was being discussed at the IETF. And so what you are seeing here on this graph, it's again on the x-axis, the number of transport segments. And in green, what you see is the compression efficiency that you are getting with microSID. And in red, what you see is the compression efficiency that you have with the alternative, that is this gzip or replace. And basically, you can see that for all of the cases, microSID is way more efficient. So better hardware scale. As we went through these deployments with Rakuten and Bell Canada, we have been able to look at the hardware, and we have been able to validate the steering of a customer packet coming into the PEC link, and steering it into a network slice with a VPN and traffic engineering for as much as 26 microSIDs. Okay, so 26 microSIDs that we push on this traffic engineering policy. Now, this was done at line rate. This was done on the NCS 57000, so in other words, Mercant Silicon, Broadcom Jericho 2 with 400 gigaports. And so just to compare it a bit, the number with MPLS, you can see that actually we are getting twice the number of segments with SRv6 than with MPLS. So the point is really not to do the comparison with MPLS, but the point is really to say, well, we have this technology, SRv6 microSID, that is really scaling. So 26 microSID is great, and to see a bit how the operators are using it. And in this same spirit of trying to go lean and trying to go back to the purity, well, in MPLS, when you have entries to a remote ISIS node, you actually have 4 entries in the data plane. And you also have 4 counters in the data plane. And so if you go with an SRv6 microSID fabric, you are simply reducing the amount of resources that you are going to use in your hardware. Better routing scale. This is also a very interesting data point that we got from the deployment from Bell. So at Bell, they had issues with the number of unique nodes that they were able to support in their SRMPLS deployment. Now with SRv6 microSID, they are able to get up to 15 million unique nodes in their network, which is 20 times more than what it was supported with MPLS. And if we look at the number of unique services that are supported in the network, with SRv6 microSID, they are able to do 512,000 services. In MPLS, if we assume 20% of the label space to 100K. MPLS does not support IP summarization, which means not only that you will have a smaller scale, but also that you will have to deal with PGP 3107 complexity to be able to carry your host routes. And then last but not least, seamless deployment. And really, this is something that Dennis Kai from Alibaba described 2 years ago in an excellent manner in the podcast that you have in there. But with SRv6 microSID, one of the key benefits is that most of the use cases will only do IP and IP encapsulation. You will not need to have a segment routing header. Because simply just by having IP and IP encapsulation, you're able to fit 6 microSIDs into the IPv6 destination address. So really, for most of the use cases, this will be more than enough. And if you go a bit further and you look at the hyperscaler use case where you have this SDN controller, the SDN controller is actually computing the path, and it's encoding it into one single IPv6 destination address, and it's passing this address to the application. And the application is not aware. The application is treating this as something opaque, but it's pushing it into the packet. So it's really easy to start a policy from the application itself. So again, from an SDN controller point of view, this is something that is super simple. Then path tracing. This is one new innovation that I would really like to have more time to talk about, but I don't have it, so I'm just going to try to give you a bit the overview of the problem that we are trying to solve. And a bit with segment routing, what we try to do is to go back to the purity. We try to ask, for example, naive questions. And so the question here that is very simple is, how come that if I have a packet from node A to M, we do not know, and I guess that many of you, or maybe all of you, you do not know how this packet has been exactly forwarded in between the routers A and M. Because in reality, we know that here we have 7 valid ECMP paths, and we know that very likely the packet has taken one of those 7 ECMP paths. But we do not know exactly which one of the packets has been taken. And to go one step further, in some of the cases, there are things like, for example, AFib corruption. And it might be the case that some of the router, for example, the router B here, forwarded the packet into a completely different path that is not one of these green paths, like the paths shown here in red. How do you know that this has happened? How do you detect this? How do you know how this packet has been forwarded? So what path tracing is trying to solve is this. It's going to give you, in a deterministic manner, it's going to tell you how the packet has been forwarded in your network. And on top of that, it's going to give you the timestamp at each one of the hops, and it's going to give you the load for that interface at each one of the hops. So To show in a very simple manner how does it work, let's say we're going to use this very simple example, and I'm going to create a probe packet that is going to go from the router A to the router M. In this probe packet, what I will have is an IPv6 header, like in an ESRv6 use case. So source address A, destination address M. And following that IPv6 header, what I will have is an IPv6 hop-by-hop header, which is an extension header to IPv6. On this hop-by-hop header, I will have the path tracing option, which somehow you can see it as a metadata scratchpad. Okay, so it's going to be a space where each one of the routers is going to write what we call midpoint compressed data. This midpoint compressed data is going to be 3 bytes of information where we are encoding the outgoing interface ID, the outgoing timestamp, and the load. So somehow you can see this, maybe like a passport is the analogy that we use sometimes, because as the packet is traversing each one of these routers, the routers are going to stamp into this passport this information. So the router A here is generating this probe packet, is going to send it out, and just before putting it on the outgoing interface, the first thing that it's going to do is going to write into this path tracing option, is going to write, well, the packet is being forwarded on the interface from A to B. It's being forwarded at this particular time, and the load that I'm seeing on the router is X. Then the packet is sent out, the packet goes to the router B, on the router B I do all my lookups, I'm going to forward it, and just before I put it on the outgoing interface, I'm going to do the same. The first thing that I'm going to do is I'm going to write the outgoing interface, so this packet is being forwarded on the link from B to G at this particular time with this particular load. And the process goes on, and so the packet arrives to the router G, that I'm doing my lookup, etc. But just before forwarding the packet out, what I'm doing is I'm writing this packet is being forwarded from G to M, on the link from G to M, at this particular time with this particular load. So the basic intuition here is to give you full visibility into how this packet is being forwarded through the network. And then on top of this path visibility, we are also giving you the timestamp and the load so that you have a full characterization of the packet delivery path. This full characterization is written with a minimum overhead, so each one of these nodes is only going to write 3 bytes of information into the packet. And with this full characterization, basically you will be able to know how the packet has been routed and the state of each one of the routers in your network. And then what we are going to do is we are going to put this information into a time series database so that then you can go back and look up the state of your network for any point in time. So to make path tracing work, the key idea is that we need to monitor in the most basic pipeline of the router. Because any solution that would actually try to monitor like for example, punting to the CPU of the router and monitoring the CPU of the router, that is not useful at all, no. Because we really need to monitor the same thing as your customer packets. And so we need to use the same forwarding tables as the forwarding tables of your customer packets. So really, the key idea is to engineer it from scratch so that it can be implemented at line rate, effective on any packet. That's why one of the key principles since we started has really been to extract the juice out of the router and try to get the most out of the router capabilities. And what this means is that we had to minimize the MPU parsing, we had to minimize the number of bytes that we return write, and not only the number of bytes, but also depth. Try to write at fixed positions so that we minimize the number of editing commands, try avoiding, for example, doing header insertion or resizing the header, and obviously minimize the MTU. So we have been working with different ASIC vendors and different ASIC architectures to get this implemented at line rate in many routers that you will see later. And so we are trying to minimize the hardware complexity by doing a very good engineering of the data plane, but we are also trying to minimize the hardware complexity by leveraging SDN analytics. So if we go back to the previous example, we had the probe packet in blue that was going from A to M. And here, when the packet gets to M, one very simple approach would be to say, OK, I'm going to process this packet on M, on the CPU of the router M. But that actually does not scale. The router M is not designed to do this processing and so on. So instead, what we are doing is taking a way more scalable approach, that is to forward all of these metadata to an SDN application. On this SDN application, what we are doing is first we are translating or we are processing this information. So for example, we are translating all of the midpoint compressed data into meaningful data. Okay, so we translate a list of compressed interface IDs into an actual path. We are deducing the timing and the load history and so on. But then also, because this SDN application has communication with the PCE, with the path compute engine, we can do quite interesting things. So for example, from the PCE, I can get the RIP information. I can get all the routing information. So I can get the RIP for each router. And from the path tracing, what I have is the information from the FIP, how the packets are being forwarded. And for example, this SDN application, what it can do is it can check whether there is any inconsistency in between the routing and the forwarding, which is quite interesting. So really, path tracing, it's something that at Cisco we are going to ship it in this calendar year. We had a very rich, very interesting conversations with Broadcom and Marvell at the very beginning of the project to design the data plane. This is already supported in Broadcom Jericho 2 SDK native. At Cisco, we have this running on the Cisco 8000 with Silicon One. We will have it shipping on the NCS 57000 with Jericho 2 Cisco SR9K. We have a very rich open source applications with Linux, FDIO, BBP. We also have an open source P4 implementation. And obviously, we are standardizing this at the ITF. So to conclude, simplicity always prevails. That is the key thing that we are doing with the segment routing project, is to try to go back to the building blocks, try to bring back this simplicity. Along the journey, we already removed LDP and RSVPT. We managed to very successfully reuse the MPLS hardware for SRMPLS, and SRMPLS was great. We foresee a lot of deployments for SRMPLS, and there will be a lot of future for it. However, the simplification journey is continuing with SRv6 microSID. And that's a bit where we are going. And more when we can deliver this with more scale and with functionality. So that's all. Many thanks. And if there's any question.
Tom from Cloudflare. First of all, thanks for that presentation. With packet tracing, I'm a bit wondering, you were explicitly mentioning this is super helpful in ECMP environments. It looks like an active monitoring solution. So how do you actually get to a point where, for example, because 5-tuple in regular ECMP environments, how do you get to the point where you know specifically for customer flows, it's going through there? Do you generate a PT packet for every single customer flow that hits your network?
Okay, so path tracing, it's indeed, well, the first phase that we are doing for path tracing is really to do this active monitoring, so we are generating probes. The idea that we have is we are going to generate probes with, in SRv6, we have what we are using for the ECMP is the IPv6 source address, destination address, and the IPv6 flow label. So we are going to use many different flow label values so that we are able to monitor all of the different ECMP paths in the network. And so that is the step one. So to really being able to monitor whether the FIP is working correctly from an ECMP point of view, and that we are using all of the ECMP paths correctly, and that we have the correct load balancing. Then as a phase two, indeed, you could try to apply it more as a passive approach and try to measure particularly customer packets. But as a phase one, what we are going to do is this active monitoring and simply just monitor that all of the ECMP paths is been working correctly.
Two simple questions. The path trace, could that be used in switches as well? Now you mentioned it in routers.
It's a very interesting point. Initially, we were thinking of routers only, but indeed, we will see. It's still very early. Like path tracing, we have only disclosed it to the ITF, and we started with it only maybe 1 year ago. But it's a very interesting piece of feedback, and we will see.
A second question, no matter if it's switches or routers, you might have some LHCP tunnels with different routes. So it would be, I wonder if the path trace goes on the LHCP interface or if it goes on the physical interface.
So it goes on the physical interface. And we consider that's enough for now. We will see in the future, but it's going on the physical interface right now.
Any other questions?
Yeah, Tom again. You had the P4 logo on your slide deck. Is there an open source GitHub repo that we can have a look at?
Yes. I don't know if it's here, the link, but anyway, on the segment routing website, there is a section on path tracing, And you have all of the open source implementations. You have a link to the P4, the Linux, and the BBB.
Any other questions? No? Thank you very much.
Thank you very much for your time. Have a good day.
Let's see, we're a little bit ahead of schedule, which is not a bad thing at all. I'd like to welcome Jonas from
Thank you.
Nokia, who will be talking about 480, 800 gig and beyond.
Thank you.
Welcome.
Hello, everybody. My name is Jonas Vermeulen. I'm running technical sales for the Nokia Web Scale unit. That's basically a unit that addresses all the hosters, the IXPs, and we basically help them defining what they can do with the network, how to grow the capacities, whether it's on an IP or WDM basis. I'm actually impressed already to see this many people after a shorter, likely shorter nights. And it's also a pleasure to meet some of the customers here after a long period of COVID, amongst which we have here our Team Blue guys, who were, where are they? They're there, fantastic, who deployed already one of those 400 gig routers last year. And in this session, I will be giving some more hints on what such a 400 gig capable router is all about, what kind of design considerations we had to take as a router supplier, as a router manufacturer, but also give you some hints in terms of how you can select such a 400 gig IP and PLS router. Now, I already mentioned COVID, and obviously that has brought us to the attention to the realization that capacity is increasing in our networks, and that is obviously funneling the drive or the increase in our networks of traffic. Now, as you're looking at 400 gig, of course, that's going to give you more capacity, but at the same time, you should likely still consider the fact that, hey, security is also an important aspect. DDoS attacks are increasing, and that means that on your peering routers, your ingress routers, you will have to still mitigate, you will still have to make sure you can address or you can stop any potential attack. And part of your consideration might also just be power related, and that's kind of what goes into the sustainability bucket. Because what we see is more and more that customers, operators, make that a key decision criteria as and when they're upgrading the networks. It's not like you can always increase your power feeds to your routers. It's not like your data center always has additional power available in the racks. So part of it is also, hey, how can we ensure that higher capacity routers don't drain your power too much, or that they're actually more and more power efficient as compared to the bigger routers as we used to have them. Now, luckily yesterday there was already a few talks about 400 gig. I mean, you've seen now this chart a few times already, that indeed the number of 400 gig pluggables that are being sold is increasing drastically. We're now here 2022, and you see already a very wide variety of pluggable optics that is finding mainstream, and that's all about both multi-mode variants, single mode variants. Single mode variants are the ones that are more popular, also more used nowadays. And you see also there a mix with 2x200, 2x100, which is also used to provide them a fan out for pluggables that if you still want to use normal KSFP28 as a breakout. Now this is the chart for 400 gig, and it's indeed like the title already said, the introduction. For us, it's also a matter of giving you some hints about what 800 gig is going to be all about, right? So, and we'll go to basically in that in a few slides from now. Now let's look a little bit more on the technical side. What does that mean now, actually building out a 400 gig capable router? And if we simplify more or less the design of a line card, you more or less see a number of building blocks, a number of key parts that are important as your as you're scaling out or as you're using such a device. On the left, you basically see just a pluggable. I mean, this is what you obviously see that you need to plug in all your cages. And that's where you have the choice of FR, LR, DR, and so on and so forth. That's going to give you a certain capability to cover a distance. It's also going to give you a certain density on the faceplate. I mean, depending on the form factor you choose. And in the end, that's also making, I mean, you need to make sure that it's compatible with the other device. That basically sits in a cage. And that cage is then connected with a SerDes link towards your router ASIC. And it's that router ASIC that you could say these are the crown jewels of your router. That could be a commodity ASIC, that could be a vendor-specific ASIC. And each one of them, each one of us has basically a different approach of doing that. What you see here is basically a Nokia approach where we've split up a Mac ASIC, different from a packet processor ASIC. I'll come back a bit why we do that, but it's basically ensuring that we get you flexibility, compatibility between different versions of router hardware. And the packet processor is obviously the part where you do a packet lookup, do your MPLS label lookups, one label lookup at a time, multiple label lookups at a time, and so on and so forth, where you have buffering and as well. Now, as the power increases of each one of those ASICs and the pluggables, it's still necessary to cool that. So on top of each one, you will see a heatsink, and you will have a massive airflow that you will have to manage within your router hardware to keep all those components cooled. Now zooming in on each part a little bit. So let's start a bit with the pluggable optics and the cage types. And what you actually see on the cages is that they become more and more universal. And you see that basically two form types more or less remain in that. On the one hand, you have the QSFP, the types that are supporting 100 gig plus type of optics. And the size of a QSFP basically allows you to support 100 gig QSFP28, 200 gig QSFP28DD, QSFP56, the 400 gig QSFP-DD, but also the same type that is being standardized for 800 gig QSFP-DD 800. And that means that if you're now looking for a router and you see those plugs, that you're basically going to have the flexibility to choose to use that port for 100 gig all the way up to 800 gig, or even do a breakout there. We see a same trend towards a universal cage and the 100 gig minus, and that means that an SFP is now becoming available SFP, SFP plus, SFP 28, 56, and also SFP-DD. It's a newer type SFP-DD, but it really is going to allow us to compress or reduce the amount of footprint needed for 100 gig plugs, right? And I'll show you a picture of that later. Now, physically, you also see that on the line itself, quite important is the evolution towards 100 gig lambda as a physical modulation method, allowing basically a single wave or a single optical channel to transport 100 gig. And that is effectively used all the way already in 100 gig plugs, but it's also the underlying technology in 400 gig and 800 gig. And the second part is around everything around ZR, basically allowing coherent technology to be integrated, built within a transceiver in the form factor of a QSFP. And there you see then the evolution where routers become more capable, or more or less take up a role also in the whole transponder networks, because it allows you to do IP over DWDM designs, which in a way is very good for point-to-point designs, maybe to a certain limited extent metro designs, and only for long haul. I mean, only you will have basically choice in metro or long haul designs to still use more of a traditional transponder design. Now, this slide gives you a bit of an overview what is 800 gig QSFP-DD all about. So it's basically the MSA. This is the service agreement to standardize the plug itself that got ratified or standardized last year. And that one you can already see in the picture, it allows you to use a very similar form factor for 800 gig plugs as compared to what you see now in 400 gig. And then on the faceplate, it's basically going to have the same size as a 100 gig plug. Quite different from 400 gig and lower speeds is the move towards 100 gig SerDes as an interface towards your ASICs and the backend, right? And that's going to be giving an important consequence on how internally your routers have to be designed. Because all of a sudden, your PCBs and your whole boards need to go for an upgraded signaling speed and ensuring that it can transport 100 gig SerDes as an electrical standard to communicate between ASICs and communicate with those plugs. On the right-hand corner, you see there the pluggable modules that will be first on market. I mean, they're more or less the shorter distance ones. And they're also plugs that allow you to do a breakout, right? Because initially, the clear channel 800 gig is I mean, that's still being standardized. So the very first plugs, they will be having the form factor of an 800 gig, but will effectively be used as 8 by 100 gig or 2 by 400 gig. And the last bit around form factor is obviously is quite an important one, which is around that power saving aspect. Because as things become smaller, you're actually ensuring that also power can be optimized. And so many times, or what you could consider is rather than using 2 times 400 gig plugs, is to just use a single 800 gig plug, maybe do a breakout, but that's actually going to save you a significant amount of power on the plug itself. To give you a comparison, a DR4 plug 400 gig will consume around 12 watts. A DR8 plug will consume more or less 16, 17 watts. Right? So, and that's basically where we come from. For a slightly bigger amount of power, let's say, how much is that? 25, 30% more power. You're actually doubling the speed, what you can get out of a port. The other plug I was mentioning is the evolution towards SFPDD, where even up to signals of up to 100 gig, you will have basically the option to use either QSFP28 or to use an SFPDD cage. And the clear advantage is that with SFPDD, you're obviously, it has the size of a normal SFP+, so you're going to get a lot many ports on the very same faceplate compared to a QSFP28. And that's how we also see the transition from, let's say, your current form factors of 48 times 10 gig plus, let's say, 6 times 100 gig. You're actually going to be seeing completely another form factor with 48 SFPDDs as an example, plus 6 QSFPDD, which is what you can all put on a 1RU faceplate itself. SFPDD itself technically uses a single. I mean, why can you actually make that plug smaller? It's all to do with the fact that you're not going to use 4 lasers anymore and mix them all together on top of a line. It's actually only 1 laser will be there, and you're going to modulate your 100 gig signal using a single lambda, so a single optical modulated signal to get across from A to B. From a distance perspective, you see the regular form factors, so you have SR, DR, FR, LR as well there. I said, like, how do you then effectively use 800 gig? One of those models is obviously connect them back to back, 800 gig. The reality is that you won't always have a lot of 800 gig routers around or 400 gig routers around. So you can obviously do a breakout. How do you do such a breakout? Well, it's pretty like what you do today. You basically either use a splitter cable or you use a certain optical patch panel or a breakout cassette so that you have an MPO cable coming from your router. You link that to a cassette or to a module. From where onwards, you nicely have like your 8 or LC connected fibers towards an 100 gig DR on the other side, as an example. Or to do the same with FR, if you do 2 times 400, then you basically split your MPO cable into LC cables, 2 LC fibers to the other end. Every time what you see there is indeed, again, the use of 100 gig single lambda. Basically, again, 100 gig modulated signal to transport your 100 gig traffic. Now, last bit, a bit around the plug itself. So the transceiver itself, you see a schematic view of what is all on here. And if you look from left to right, you basically see on the left-hand side the photonic driver, which is basically your pump or the place where your laser is. It converts your electrical signal into the photonic or into a light-switched signal. And that's where you also need your 100 gig signal lambda. That's where it all comes into and what is being standardized already. The grunt or the real work is being done on the DSP side. That's where all your FAC is done. That's where all your modulation is being calculated. And that's also the place where most of the power is being consumed. And then on the right-hand side is your attachment unit interface. And that's basically that attachment on your PCB that ensures that you're getting like your 100, your 400, or your 800 gig traffic from like your router ASIC itself. What is important here is that on 800 gig, it's moving on to a 100 gig SerDes interface, right? IEEE is standardizing, you see the number there, you can look that up. But that's, as I said, is a quite significant step up from the way how 400 gig transceivers are realized, because that's only using 50 gig. Now, what is SerDes now? I mean, as said, it's a connection between your ASIC and a cage. And you see that from, as technology evolves, you basically see there 10 gig moving on to 28, 56 gig, now basically 100 gig. And if you then look at the line, it's effectively using now also PAM4 on your electrical signal. So it's not anymore just a black and white signal, it's actually a PAM4, which in a way is increasing complexity on both ends. But at the other side, it's, well, reducing symbol rate. So you're still keeping your 56 gig of symbol rate. But yeah, that additional complexity will allow us to have higher I/O and will allow us to support those higher speed pluggables as well. Now, why is that important also, that 100 gig SerDes? Is because that needs to link up to your router ASIC. And I said that router ASIC then needs to work on 100 gig SerDes. You have then there the option as a vendor to bundle that all in one big chipset. I mean, some certain Broadcom chipsets do that as well. What we as Nokia have done with our own silicon is to separate out what we call the MAC chipset, which is your media access chipset. It's basically where your front end, your media speeds are defined and where they are supported, and your packet processing chipset. On the MAC chipset, why do we do that split? Is because it allows us to create much more flexibility and evolve faster in supporting new speeds, to create flexibility there, to do more things that are only related with like your interface itself. So what do we do there as an example? We allow for intelligent aggregation, which is a way for us to do pre-buffering to catch like microbursts and so on. I mean, they have nothing to do with like your packet processing, so it's kind of nice if that is split off. We do a certain level of QS processing there already. Things like FlexE or MACsec can also be implemented there. I don't know if FlexE is a common term, I mean, but it's basically a way for combining multiple, let's say, optical or 100 gigs that you have on the line into a logical higher speed interface in your router. So that means that if you were to configure a 4 or an 800 or even for us a 1.6 tera logical IP link, that down on the line it could be realized as up to 16 individual 100 gig links. And that could be useful if you're, as an example, your transponder or your optical network doesn't quite support the higher speeds yet. At least you can realize them with lower speed links. On the right-hand side, what is important as well, if you're choosing routers, is how you want to have your memory implemented, right? On that packet processor ASIC, the biggest chunk is memory there. That memory is used for QoS, but is also used for any kind of memory lookup. That could be FIP lookups, that could be ACL lookups, that could be label table lookups. And you want to make sure that it can all happen in a single pass. I mean, the worst thing is that indeed you need to do packet recirculation because you can't look up enough labels at a time, or that you can't process enough ACLs at the time, and your peering router, maybe you have 1,000, maybe 100,000 ACLs, and then you have to recycle your traffic, right? And that would cause delay in your forwarding. So important is the quality and the speed of your memory that you have on board of such a router ASIC. Now I said cooling, and we come there to the last part here. Cooling, in a way, those line cards, every part consumes more power. So how can you deal with that increase of power and heat production? On single appliance system, I mean, there is only so much you can do. You just have to have a lot of air going from front to back. On chassis-based systems, basically the evolution has taken place to go from a mid-plane or a back-plane design to basically have an optical cross-connect design so that air can flow faster and better through it, and that each component can individually be cooled. Again, on power, what is another method of making sure your line cards can be cooled? I mean, part of it, why do we have to do something special there? I think what you see is that as the evolution of pluggables goes forward and higher speeds are basically standardized and brought to market, you see that the individual power is just going nicely going up. And I mean, you see a bit of a trend line, but there is basically no way going back. I mean, 100 gig was, QSFP 2800 gig was quite low here, was nice. But now here we're looking at 400, 800 gig, reaching values above 15 watts, over 20 watts. If we think about 800 gig coherent, we're even looking at 26 watts, right? What do you need to do on the line card for doing that? I said you need to push a lot of air to cool that, but part of it can also be just an engineering solution with, rather than having pluggables stacked above each other, to basically build them on each side of the PCB and making sure you can basically have heat sinks that go right on top and below your transceiver pluggables itself. And that's also, if you look at the top, that's kind of your most straightforward way. This is stacked SFP cages. That's what you see on most appliance systems, most commodity switches as well. But what we believe is that if you want to enable 400 or 800 gig on all your ports of your switch or your router, then you need to go basically with an approach where you do what we call a belly-to-belly SFP cage design, right? And we see that in certain examples. I mean, otherwise there is no other way you can have ZR optics or even the 800 gig variants across all the ports in your router. So with that, I'm basically come to the conclusion of this session. Basically, what I've explained to you here is a number of design considerations, a number of things that you can keep in mind around when you select a platform. A few things around platform, mechanical design, power, cooling. Give you a few hints around what is important around data plane and chipset design as well, and give you some further detail on the optical transceivers that you could use to support higher speeds. And with that, I thank you for your time and attention, and open the floor for questions.
Let's see, who's first?
Hi, Rory from Google. In a few slides ago, you had a graph of up and to the right of power budgets. So
This one?
yes.
Yeah.
Doesn't that imply like increased demand for cooling? Do you see
It
a
does.
point where we have a problem with cooling and can't move forward?
It's going to be an interesting challenge, both for us and for the transceiver producers, to ensure indeed we can make somehow a ceiling, or we can indeed define a dip in that. But this is basically what is being standardized at the moment, what we have in view. And yeah, that's more or less what we can design for at the moment. I think it's going to be interesting indeed, because I mean, after 800 gig, we see already certain manufacturers going now to defining 1.6 tera. How that yeah, how the power budget for those transceivers was going to look like. Thanks.
Any other questions?
Yes, thank you. I was wondering about the spike to the left side. What happened there? I'm not in the transceiver game.
That's okay. Basically, it's a bit of small font here on the slide, I suppose. But I mean, this is a CFP cage. So as 100 gig was being standardized, or as technology was evolving and 100 gig came on the market, initially it wasn't possible to trim that down or to compress it in a QSFP form factor. So it had to be the bigger CFP cage, and that by itself just required and demanded more power. The DSPs back then were just not as good, as powerful. It needed to just have more power to modulate that 100 gig signal. And that's basically why you see that spike here. Luckily, QSFP28 came around, and we're all enjoying that, 3 or 4 watts that 100 gig needs now.
Do we have any other questions?
Henrik Kramselund from Security. I'm doing a lot of security for enterprise customers, and I think it's all nice and well with 400 and 800 gigs. You forwarding a lot of traffic to enterprise customers, and some of that traffic will be unwanted. Can we expect the feature set and wire speed filtering to be available for these?
It's a nice question also for us, because our rate, I mean, there is a clear difference there between what kind of chipset you have in your router. And we see that also in our own benchmarks. What we design our chipsets for, the Nokia chipsets, is to maintain ACL filtering capabilities at the line speed at the same rate that you can push traffic through, right? So for us, we ensure that we do that single lookup through the chipset to cover our whole ACL scale, right? And for us, that's 256K ACL entries on ingress. So we make sure that it's actually done at line rate. And whether you do it at 4 or 800 gig, I mean, line cards itself, they're going now to around 18 tera per line card. And we actually make sure that is all done properly. And then that covers your ACL capabilities, what you can expect from a router. So it's everything layer 2 to layer 4, and to a certain extent also packet, well, looking deeper into a packet.
All right. Any further questions? No? I guess we'll have a very long break now. We are a good deal ahead of the program. The program committee will just talk during this break whether we'll do the full break or not, so listen out for the bell if you're out there, but at least the amount of time plus a little bit more you can expect. So thank you again, Jonas, for the excellent talk. And just before you go, the T-shirts are already set up there for you to get if you haven't gotten it already, and the surveys are up already as well. So please remember to fill them out and have a good break.
Welcome back, everybody. Welcome back, everybody. Hope you're all having a good morning. The headaches are still keeping away. We've pulled the sessions forwards very slightly, so we will be having lunch at 12:15. The kitchen may not be quite ready then, as we pulled it forward quite a bit. So we may have to wait a minute or two, but that's our hope, and then we'll finish earlier. Anyway, meanwhile, we have Tomek from ISC, who's going to talk about Kia 2, which is the wonderful new replacement for everybody's friend, DHCPD. Thank you.
Hello, everyone. I'm Tomek Mrugalski, and I'm a DHCP guy. So I got involved in DHCP in 2003, so that's almost 20 years. So it started as my master thesis. I implemented something called DBLR. It's been around 20 years ago. Getting a DHCP v6 implementation was a bit uncommon, but it was there. I kept developing it. So in 2011, I joined ISC, and they showed me, how the DHCP is really used. So back then, when it was my own personal project, I had like idealistic approach. So it was IPv6 only. So there was no support for legacy technologies like IPv4. You couldn't configure anything with IPv4, but in real networks, people still use it. So once I joined ISC, and they told me, okay, Tomek, we really need to, focus on DHCP v4 as well. So the implementation that ISC had back then was IC DHCP. So I hope most of you know this. It's DHCPD. It comes by different names. But anyway, this software has been around since a very long time. So the first commit was in 1995, and many of the design decisions that were made, like in mid-90s, they were okay for back then, but they didn't stood the trial of time. Like there are some code optimizations that are doing crazy things to save 2 bytes. And maybe it made sense back then when servers had like 16 megabytes of memory. But right now it's completely crazy. But the craziness is still deep inside in the code. So it's very hard to maintain. Also, the API that it has, it's OMAPI. So you really need to be a C programmer to understand how to use it. And it has a lot of limitations. So that's something, yeah, in the 90s, maybe it was okay. But right now, no way. So one of the first things that I was tasked with when I joined IC was to evaluate what part of the code needs to be refactored or rewritten. So and the conclusion was that we can maybe reuse the header file with the option codes. And that's basically how Kia had started. So it's a clean implementation from start, using modern technologies. So, but anyway, I'll be talking about Kia a lot in a couple minutes. But with ICDHCP, we are trying to sunset the project. I know that's it. A lot of users are still depend on it, but now it's time to consider migration. So the release we did in March 4.4.3, this was the last one that was using client and relay. So right now, the upcoming releases will be server only, and it's in maintenance mode. That means that we are not actively developing it. We are not fixing small bugs, just critical bugs. If there is anything security related, or a customer comes to us and say, hey, this is critical for us, it's breaking down our usage model, can you fix this? Then yeah, we're fixing this. But it's like very slow process. It's complicated code. It's very difficult to test it. It's very monolithic. So it's a slow process. So anyway, if you are still using the old implementation, consider this a technical debt, and you should migrate to Kia. So and to encourage you to do it, there's a couple of things. First, we developed something called Migration Assistant. It's basically the old DHCP run in a special mode that it loads the old configuration, and then instead of starting the server, it prints out the JSON configuration that Kia can accept. So it can cover like maybe 80% of all the use cases, but it's really not possible to cover everything because the config file of the old implementation, it's really a programming language. So you can have variables, you can have functions, you can have recursions and if-else statements. So this is like Turing complete. You can probably solve Towers of Hanoi in it. So so if you went overboard with your configuration, yeah, that's something that cannot be migrated to Kia automatically. So anyway, there's a nice talk that Alan Clegg gave during DKNOG, so it's online. I encourage you to take a look. So what are the major differences between Kia and IC DHCP? So the first one is we have a REST API, so, and it's extensive. There's right now 184 commands you can do about anything. So, and this is online configuration, so you can use it the old way if you want to. You have a local config file that's loaded, you can kill it or restart it or whatever. But you can also modify the configuration on the fly. And there are lots of API commands. You can do config get, config set, but also modify something like add the subnets on the fly, add reservations for the devices, look at leases, or do something with the leases. So we also have a concept of backends. So the leases, reservations, and server configuration, you can say, okay, I want to keep everything in a local file, and the local storage is CSV if you want to keep it small. But if you want to go bigger, there's support for MySQL and for Postgres. We used to have support for Cassandra, but it didn't work too well, so we removed it. Also, the concept is slightly different in the sense that it's modular. So we are trying to keep a reasonably small core and then optional hooks. And the hooks is something like Apache modules. If you need some extra functionality, you load them. If not, you simply skip them. So there's there's a well-defined API for the hooks. So and right now there's I think 18 hooks that's provided by ISC, and there's over 10 more on GitHub implemented by community around it. And there's many more that are private, so people are developing something in their own and choose not to share. So that's also an option. The code is open source. This is under Mozilla, and we have some commercial add-ons. So if you want to support the open source, it's a very nice gesture if you buy the extra fancy stuff. This is available as source, so if you want to compile it on your own, yeah, that's possible. But these days, most of the people just want the packages. So yeah, and we have plenty of packages for almost everything, except CentOS 8, which broke down. So, but we are working on it. So we have stable and development releases. So if you don't like to upgrade frequently, we have roughly once a year a stable release. And we have monthly development releases. So if you want, the bleeding edge, this is also an option. So the REST API, it's JSON-based. So you can send JSON structure, and you get a JSON response. And this covers everything. So this is a small part of the list of the commands. So each of the command is well documented with examples, expected responses, and so on. So this is how you can use it. So we provide a tool, Kia Shell, which is really an example Python script. So it's okay. There's some fluff in it, but this is like maybe 10 lines of code. So you get a JSON, send it over HTTP, or HTTPS, and then you get JSON in response. So we can do this in about any language. And this is how you can send a simple command, get me a list of supported commands, and then you get a response. And from that, you can then start using more complicated commands. So what's with the backend? So as I said, if you want to, you can go small, use a local CSV file. So it's similar to the old DHCP, but CSV is easier to parse. So the old DHCP had like a special custom format that was not that easy to parse and complicated. And if you modified something, there were like uncommon structures there. It was complicated. Here it's a basic CSV file. You can parse it with a couple lines of code. But if you want to, you can use a database. So with the database, the nice thing is that it's completely online and Kia doesn't cache anything. So if you tell Kia, hey, store leases in a database, you can modify it. Like, for example, your cable modem broke, you send a technician to replace it, and you know that you can remove the lease. So you can just go to the database and remove the entry, and Kia will pick this up instantly. Also, you can do the same with host reservations, and of course, there's an API if you want to use it, but tweaking the database directly, it's also an option. So it's also nice that with this you have all the powerful tools that you can use with a database, statistics, reporting, and things like that. So with backends, there's like 3 separate aspects of running a DHCP server. The most frequently changing are leases. So if you have a busy network, that's something that happens like thousands times per second. The next thing is host backend. This is the host reservation. If you want to do this, some networks do it. Like for example, if you want to control over which addresses your customers are getting. So every time the customer signs up, you add a host reservation. So, and then finally, the least frequently changing aspect is configuration backend. That means like options, subnets, share networks, global parameters, or option definitions, and stuff like that. So that typically doesn't change that often. And anyway, in Kia, each of those aspects is configured separately. So if you want to store some of them in a local file and the rest in a database, this is an option. Okay, so what are the recent changes in Kia 2.0? So we did a lot of work around the performance. So I'll be talking about this in a minute. We added proper support for TLS and also cache threshold, script hook, and we started work on dashboard. So to understand what we did with multi-threading, a bit of history. So in Kia 1.8, we implemented multi-threading in the packet processing. So if you used a single server that processed packets from the devices, this was very performant. But most of the people are using HA. So you have a pair of servers, and then they need to update each other with the lease updates. So, and that part, unfortunately, was still single-threaded. So the packet processing was very fast, but most of the time it was waiting for a response, which was sequential. So we had a Unix socket connected to control agent, and then a single HTTP connection that was also sequential, and we waited for a response. So it was like half multi-threaded. But in Kia 2.0, we solved this by changing how the servers connect. So you have multiple threads. Each thread opens its own connection. So you have multiple connections with multiple threads doing the updates and multiple threads doing the packet processing. So now it's fully multi-threaded. You can take advantage of multiple cores. And The performance gain from this is substantial. So these are the performance numbers that we got on our test setup. If you're interested in the details, the link is at the bottom. There's a lot of detailed information. So, but anyway, in many cases, like for example with MySQL, we got over like 15 times. In some cases, even like close to 20 times faster. So this is like a really huge performance improvement. So with TLS support, previously we had like sort of fake TLS support. You could set up a reverse proxy, but this was not really a proper TLS support. So in 2.0, we implemented native support, so you can have 3 modes. Okay, actually 2. The first one, disabled, is not really a mode. So, but anyway, you can do encryption. This is where the client verifies the server. This is the typical thing as you would expect when you connect to a bank or a website. But we also have the strong model when there's mutual authentication. So the client verifies the server, and the server verifies the client. So and this is the default if you enable TLS. So I think it's nice, you know, like security-oriented default. Although it might be more complicated because you need to pay attention to the client certificates. So in Kia 2.1, we also implemented support in MySQL. So in the sense that if you want to connect to your database over TLS, that's also possible. With Postgres, this requires only configuration changes on Postgres and the database, so it doesn't require any Kia changes. So it used to be working in the previous versions as well. So okay, moving on. What are the other additions? We implemented cache threshold. So what is it? The problem is that there are many buggy DHCP clients. So I'm sure you all know, but in the DHCP protocol, there's a renew timer mechanism. So the server tells the client, hey, you get the list for like 2,000 seconds, and after 1,000 seconds, you are supposed to start renewals. But some clients are broken, and either they have like miscalculating or sending the updates immediately. So, and this is annoying. So we had one customer that said that 9% of his clients generated 50% of the traffic. So, and this is a problem because every time Kia gets a list, it was doing the full update with all the lookups, logging, updating the partner, and then the client was repeating the same thing after next second. So, and over and over and over again. So we implemented a cache threshold. So you can say that, hey, in the first 25% of the lifetime, or you can express this as seconds, so in the first 10 minutes or whatever, if the client comes in, we'll not do any update. We'll just send the old list, just shorter. So, and then we can not update a database, not send the updates to the partner, so it's much, much quicker. It's still not a complete solution. You know, the crazy clients are still there, still sending packets. We still need to process it, but it's well, I would say it's not a solution, it's a mitigation. So the proper solution would be to fix the clients, but this is something we cannot do. Okay. So another thing that that is becoming popular is that there's always requests from people wanting to do something special with the DHCP server. So the most typical one is in DHCP v6 when we do prefix delegation. I want to update my routing table, or I want to notify something, or put something somewhere. So we came up with a mechanism to call a script, and then all the data, all the parameters that are in packets are available as environment variables, and then you can do whatever you want with it. So it's not super performant. The performance numbers that I showed you, like thousands of packets per second, you cannot expect Kia to start thousands of processes and still, you know, be able to keep up. So there is some performance implication here, but still it's a reasonable trade-off in many cases. And also, my recommendation is that if you really need highest performance and do something special, the easiest way is to write your own hook. Okay. So moving on, what else? We've been working on a web interface to Kia and also to bind, but right now it's focusing on Kia. So the idea is that right now it's a dashboard, so it shows you what's going on with your server, but you cannot change anything. That's coming up. That's something that we are working on, that you will be able to change the configuration, and then sometime in the future it will be evolving towards an IPAM. So the idea is that there is one storage server in your network, and however many agents you need to deploy. So one stock agent monitors one Kia deployment or bind deployment. So it can collect the data and aggregate and send it. Also, there's an ability to export the data, the statistics to Prometheus, and then show this in Grafana. So what it can do, like basic stuff, show the version, the build, list of hooks, the CPU utilization, memory utilization. So this is like pretty typical stuff, but also has some very DHCP specific, like subnet utilization, what are the HA status, what are the failures, what exactly failed, and when and why, and in what way. Statistics for how many packets were sent back, how many requests were declined. Also, there's a configuration viewer and inspection of database connections and so on. So this is one of the screenshots. There's a lot of different panels. So of course this is web-based. So, and here you can see what's the pool utilization, for example. And this is how we can present the HA status. So what exactly is going on, how the relationship looks from both servers. So, and this is also interesting if you have like some of the failures when there's connection in only one way. It's sometimes tricky to debug. So, and then, of course, since you can export the data to Prometheus and use Grafana to visualize this, we provide dashboards, but it's super easy in Grafana to tweak it to your need to do whatever you want with it. So, the participation is welcome. So, if you have feedback, questions, requests, bugs to report, we have our own GitLab. There's also a mirror on GitHub, but we are not using it actively. So, yeah, so that's basically it. So, any questions?
Thank you, Tomek. Any questions? You're not going to get lunch any quicker if you don't.
So my name is Morten. I'm from SmartShare Systems. I was wondering, of course, the Kia supports option 82, so it knows what interface the request arrived on, the DHCP request. Is it possible to implement a hook, or does it have a hook where the DHCP packet is not with option 82, but it's maybe encapsulated in some proprietary format, and it could decode that and pass it into Kia?
Yeah. So depending on how proprietary it is, it's like, does it still look like a DHCP packet, or?
Let's say it's the DHCP packet and then some proprietary data at the end of it describing the interface or something.
Okay, yeah, absolutely. So there's first there's something called Flex ID. So typically people identify the devices with MAC address, but in some cases they want to use a different part of the packet. contents of the option 82. So, and in Flex ID, you can say, take option 82, take sub option 2, and use the value. So that's something that you can do out of the box. And if that works for you, that's great. If not, if there's something like at the end that's not even a DHCP option, you still can do that. So the first hook point that we have is packet for buffer for receive. So you get a row buffer, a stream of bytes, and then you can do with it whatever you want. Like for example, one good use case was that there were some broken clients that sent some options incorrectly. So you can fix it before Kia starts to parse it. So in your case, you can parse it and say, okay, this is like, get this part and put it in option 82.
Okay, great. Thanks.
Any more questions? Thank you very much, Tomek. Yeah.
Thank you.
We're now going to have a 15-minute wait until lunch, and then we'll come back at 1:15 for the final session. Lunch is as yesterday, it's in the restaurant areas, and enjoy. Oh, and don't forget to fill in your surveys. Well, there's yesterday's and today's and the overall one. Yeah. Don't think we don't give you choice.
It's okay? It works? Blah, 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 blah.
Ladies and gentlemen, the conference will start in a few minutes. Please take your seats in the plenary. Ladies and gentlemen, the conference will start in a few minutes. Please take your seats in the plenary. Ladies and gentlemen, the conference will start in a few minutes. Please take your seats in the plenary. Ladies and gentlemen, the conference will begin shortly. Please take your seats in the plenary. Ladies and gentlemen, the conference will begin shortly. Please take your seats in the plenary. Ladies and gentlemen, the conference will begin shortly. Please take your seats in the plenary.
Got your talk, Well, welcome back, everybody, from lunch. Hope we all had a good lunch. 2 more talks to go, then you're free to escape. 2? Well, and a closing. Go. Anyway, next up is Frederick. You may know him as Frederick or other things. He's with AWS. He's going to do a talk on peering within at AWS. I saw it last week. It's a fab talk. I hope you enjoy it. Ask lots of questions afterwards, even the hard ones. Frederick.
Thanks, Fergus. Yes, hi. So I'm Fredrik Korsbäck. I need to check my title here again. Senior Infrastructure Business Developer for IP and Interconnect, or BGP guy for short. Most people know me maybe as Hugge from the internet and IRC. Since I work for the corporate overlords nowadays, I'm not allowed to use internet nicknames in my presentations, but I guess the people that know, they know, right? So I'm going to speak a little bit about kind of what's new in the AWS Edge Network. I was not even supposed to speak here today, but there was someone that couldn't come, so this is actually a talk from last week, from Peering Days in Athens. So yeah, this is the second time that this talk has been had, actually, so which is quite unique, since AWS is not a big company that actually talks in these type of conferences. So I guess in that sense, you're privileged. All right. There we go. So we kind of first need to start with a small primer, right? It is like, what is the cloud, right? So and it is a bit unclear, even to me, what it is. Even I've been working with it for like 3 years, right? So we will start a little bit with names and kind of how we define things, right? So the first thing we need to understand to be able to understand how peering works for AWS is kind of what is a cloud, and our region, as we call them. Today we have 26 coming up, or we have 26, or span over something we call availability zones. So one region consists of at least 3 availability zones. So for example, in Stockholm, we have one cloud region called EU North that is typically serving customers in the Nordics, but that consists of 3 availability zones. And then we have kind of like our first ones, the one in the US, so Northern Virginia, Ashburn, typically known as US East. You know, whenever US East goes down, basically the internet goes down. And that consists today of, I believe, 9 availability zones. So we're building these and we're building them out. We're building them across the globe. We are in every continent right now except like Antarctica. We are everywhere and we're building everywhere. And this year we're building Australia, Canada, Israel, Switzerland, more in India, New Zealand, Spain. And so that's kind of what we're busy with. And kind of from the beginning, you know, is like, what's in the cloud, right? So it was like EC2 instances, perhaps, is something that people are aware of, basically like a virtual instance. But today is actually over 200 like fully featured services. Is that everything from, I don't know, blockchain is apparently something that people find useful, right? And quantum technologies, media technologies, you can buy basically any type of resource that helps you with your IT workloads in general. And this is something that's being expanding all the time. And looking at traffic graphs, it seems that it is quite popular. So speaking about regions, these are the ones that are currently in Europe. So in Stockholm, everything is called according to their airport name, by the way. So in Arn, which is Stockholm, we have one. We have a really old one in Dublin as well. London has been around for a long time, Frankfurt as well. CDG, or Paris, is one of our newest ones. Same as with Milano in Italy, right? So, and this year and the next year, we will build out Madrid, or it's actually not in Madrid, but it's called Madrid for now, Frankfurt and Israel. And then, as I said, across the globe, we have a couple more. But to be able to support these cloud regions, we do have a network, right? And we have something that we call the Edge Network, which is the department I work for and what I care about. I don't know anything about the data center, like what's happening in there. I work for the ISP of Amazon, right, which is 16509, recognized in the BGP table as that. So we have 310 global POPs. We add about 10, 15 a year, I would say. Some of these also consist of many POPs in the same city. I guess London is a good example where we have 9 edge POPs. And Stockholm has 2, Copenhagen has 1 in interaction. So that is kind of how we define a POP. And in this POP, we also have services. Like, it's not always about these massive mega-scale cloud regions. Because what also, like, these cloud regions that we built, the 7 we have in Europe, like, they are massive. Like, we buy land, we buy, our own power plants. We connect directly to the grid. We buy PPA agreements, so power purchasing agreements for thousands of gigawatts, right, and megawatts. And we are the largest corporate buyer of power purchasing agreements in the world. So these are massive builds, and we typically do them from the ground up. But in the edge, we have other stuff. So the Cloud4 CDN, I guess, is our oldest and most known edge service. So it is a multi-petabit CDN. Works and performs much like any other CDN you would know, and serves the same type of purpose in customers. So it's everything from streaming, which I guess is pretty obvious, like Prime Video and other streaming services are there. But always, if you use Slack maybe, like that picture probably also comes from a CDN whenever you send memes to your colleagues, right? Like that actually comes from a CDN most likely. And if you log into your bank, maybe like half of that web page is being shared from a CDN. It's not like we did, in the 90s where it has like a single Apache server and everything gets served from that. Like that doesn't happen anymore, right? Like much more dynamic things. In the edge, we also build security. So we build like web application firewalls. We have DDoS services. We have the Route 53 DNS service, which has been around for as long as we've been around, basically. We've been adding a couple of cool acceleration services the last year. So they're like all types of application accelerators that do unicast, that also ignore some of the routing constraints that we have in terms of that we do geographic route scoping. Whereas if you peer with us in Europe, you will not get our US routes and vice versa. So the acceleration service is something that kind of can work against that, right? It's a very popular service to use for like gaming, finance, and those kind of things. We also add in computing in the edge, or actually had for a long time. So we call Lambda Edge, which is like a serverless thing, which basically you run scripts at our CDN POPs at the edge to get closer to the customer. I also want to address something called an AWS Direct Connect. I think this is one of the most common questions I get when I'm out at peering conferences or talk with people, with peering people, or with like business development type of people at ISPs. It's like, what is the difference between peering and the Direct Connect service, or the Cloud Connect service, or from other companies, it could be called something else. Basically, it is a paid peering type of setup with AWS. But like, what do you get for that? So you get MaxSec if you want to, so you can run end-to-end MaxSec, which is extremely important for some customers. You get SLAs and QoS, which on regular peering, there is none. It comes with VLANs. So if you're a direct customer, you get your own like internal network in AWS delivered over VLANs directly to you. If you're an internet provider or ISP, then you're probably a DX partner, which means you're a reseller of DX. And then you get Q&Q tunnels and all that kind of stuff to deliver to your customers. And it also comes with a price list, as I said. Like, this is not a free thing. This is something you pay for. And it works well with peering. They fulfill different purposes, so they are not mutually exclusive or anything. It rather depends on what type of customer you are and why you are using AWS. Okay, cool. So to be able to support this edge network, we have a picture of the European edge network here. We are in most countries in Europe. There is a couple of countries up here. Oops, that was the wrong button. There is a couple of countries up here that we are not in right now, and I think the timing for that is not ideal right now. But we are building out more. We are building denser in most of these countries as well. And all of these are connected with backbone. We buy dark fiber and all that stuff, of course. So we have a pretty, I would say, a pretty good strategy for Europe, or like good coverage of Europe in general. Then it's the new things, right? So that's kind of what I'm here to talk about, right? So what we're doing, we're building something called local zones. Like the difference between a local zone and the one I mentioned before, an availability zone, is that a local zone is much smaller and we deploy it much closer to the end user. In theory, we could say that we actually deploy these in the edge. That is not always true. They're not at the same site, but they are at least in the same metropolitan area. So as you will see, we will build one in Copenhagen. It is in Copenhagen, but it might not necessarily have to be in our edge POP, but it will be directly connected to it. What we'll do here is that we'll bring out like a lighter version of what we offer in the big cloud. So like EC2 will something will be offered, some of the Kubernetes services, some of the like easy to maintain and easy to consume type of services. Like for example, S3 is not here because S3 is a very specifically built service that is relying on geographic redundancy. But local zones come in one, which means that a service such as S3 doesn't really fit in a single local zone type of build. All of these local zones also ties back to a parent region. So, for example, the one in Copenhagen belongs to the Stockholm region. So some of the central functions will be run from Stockholm, whereas the actual compute will run in Copenhagen. And this is actually a very popular service. We launched it actually 3 years ago, I believe, in the US. And we sold out of all capacity before the sites were even built. So that's why we're going pretty big here, and we are like blanketing the map, basically the whole globe with these local zones. So I believe we are building about 80 of them in the coming 2 years. It will use existing connectivity, so if you're already connected to us, either with the private links or with transit or over IXs, you will get immediate benefit as soon as they're done. So there will not be new connectivity or anything like that. There will, of course, be some customers that prefer to do this over direct connect if they need to have it inside their security perimeter or something like that. But in general, it wouldn't change really much for anyone here. The good thing is that hopefully we will see a lot of the compute move out to these local zones. So today, if you're a Danish broadband customer, right, and you play a game that happens to run on AWS, it is very likely that that game will be played in Stockholm or maybe even in Frankfurt. But in a year from now, maybe that game actually gets played in Copenhagen. There's another also very confusing product called the wavelength zone, which has absolutely nothing to do with the DWDM wave. So whenever the product managers told them that they had a perfect name for a service, us in the transporting and networking department was like, please, that was a bad name. But it was already decided, the prints were already made, the pens were already printed, right? So it is now called wavelength zone. And it is a similar model as a local zone, but we deploy them directly in the 5G aggregators. So we have today a partnership with Verizon, Vodafone, KDDI, and SK Telecom. And how it works is that we put a small version of the cloud, a local zone, directly in a 5G aggregator, wherever they are, right? So they can also blanket the map in a country with those. And then our customers can buy their instances in a certain ISP's 5G aggregator. Super interesting for gaming, super interesting for finance, super interesting for other low latency sensitive applications like IoT and machine learning kind of things, because those will typically be available as well in those wavelength zones. So that is something that's being built now. I know there's already a couple of them up in Germany in Vodafone's network, same in the US with Verizon. And I think it's a pretty cool product. It's cool that we can also work with ISPs on a more strategic level and not have this, because also a revenue share type of model, right? So it's like both the ISP and we can earn money here, which I think is great, and not the whole perhaps one-sided discussions that would have up to now. All right, so local zones. So in Europe, we are building them in Copenhagen, Oslo, Helsinki, Warsaw, Berlin, Amsterdam, Brussels, Prague, Munich, Vienna, Athens, and Lisbon. So that's quite a lot of work for us. And we intend to have this done within 2 years, I would say. That is at least the roadmap for now, but of course everyone knows supply chain problems and all these kind of things, so we'll see. Some of these have come a long way. Some of these are not even started to be built, but the idea is to have it done within 24 months. So we will have traffic shifts because of this. Hopefully we will have more traffic move locally, which is kind of our intention. All right, so let's speak about network edge technologies a little bit. It's very important. I always have memes, right? I'm not allowed to have memes, but I kind of inserted it anyway, so let's see if I get fired tomorrow. But if this is our general idea of network edge technologies, back in the days, we had refrigerator-sized routers, and we put a cloud behind it, and then we put peers in front of it. That was kind of the general idea. Today, if you mention chassis-based routers at our company, you'll get fired, right? That is a fireable offense to mention, redundant routing engines in a router with a backplane. There's door is over there, guys. So today, everything is pizza boxes. We built everything as we do in a data center because we are pretty good at building data centers. So now everything has to look like a data center, including the edge. So we build spine leaf technologies with one rack unit boxes. And since everyone already has been talking about 400 gig today, I guess I have to talk about 400 gig too. kind of close the circle here on every other talk of this event. So looking at 400 gig, right? So we have been a big user and supporter for it for a long time. Like back in 2020, we launched native instances with 400 gig for the machine learning people and the kind of NVIDIA GPU type of users. So they have native 400 gig in the cloud where they can run 400 gig streams directly from those to storage or whatever. And today there is even more 400 gig native products. Like you can buy Linux VMs with 400 gig networking directly attached to it. And we've been running 400 gig in a data center for a long time. So at our type of company, right, it always goes, we start with the data center. That's where all the cool stuff happens. And then we kind of take the cool stuff, move it to the backbone and do cool stuff there. And then we that work in the edge, we kind of get it, we kind of get the scraps, right? So since I'm here talking about it, it's time for us to also go 400 gig, right? Like data center has been done for a long time. Backbone has kind of been done for a long time. So let's do edge now. So like because data center kind of already started on the 800 gig cycle. I believe it was the Nokia presentation, right? We spoke about 800 gig, and it's like, yes, we are there. Like it is not the future or anything. It is like that's what we do today in the DC, right? And from basically today and onwards, there will be more and more sites of these 300 or so, 10 that we have today, maybe 315 tomorrow. We'll have 400 gig support. And when we add the 400 gig support to a site, we change the whole site. Like we don't do, because as I said, we can't like add a line card to a chassis-based router or add a box over there. Like we change everything. So we have generation cycles, right? Like everything goes out, new stuff comes in, and then suddenly you have a 400 gig site. Last week when I was at Peering Days in Athens, there was a lot of talk about optic standardizations, and I guess there was some talk today about that as well. And the only thing that we will support in the edge is 400 gig LR4. We will not support any 8-lane optics. If any vendor here tells you that 8-lane optics is a thing, fire them, or get a new vendor, right? Like 8-lane optics on 400 gig, no. Like on 800 gig, sure, it's 8 times 100 gig is cool, right? Because we want to use 100 gig SerDes, right, in the future. So on 800 gig it makes sense with 8-lane, but on 400 gig it's only 4-lane or nothing, right? We are super happy to do LR4. We will not support FR4. Like despite what some like early IXs and some ISPs have been trying to do, but we truly do not believe in 2-kilometer optics. One of our biggest costs in the network is troubleshooting cross connects. Like that is a small country's BMP for us, right? So we've always supported 10-kilometer things, right? If we're gonna dial this down to 2 kilometers, that means we will have 80% more problems in that area, right? Since we have 80% less reach. And like that's not gonna happen, right? So it's like, we rather wait it out until the right technology is there, which we believe it is not right now, in the terms of 400 gig LR4. I'm also super happy to look at ZR+. The plus one, as we heard yesterday, is still, you know, it's not super easy to do, but ZR is a standard, it is interoperable. We already use it. We have it everywhere in the metro. We use it for all type of metro connectivity already. So for us, it's basically free technology that we can use. Like it's already been verified. We have a multi-sourced vendor, you know, optics, because we can't just have a single vendor. We need at least 3. And whenever we buy something in the range of like 10,000 of everything. So ZR is cool. And if someone wants to do it, I'm more than happy to try it out. Like we haven't really used it in the edge yet, but I'm happy to do so. And hopefully we can do that together, right? And yeah, so if you have 400 gig plans, regardless of who you are or where you are, I'm super happy to take feedback and kind of, because I'm leading the 400 gig strategy internally, globally, right? So it's like if you have ideas in this field, like let me know, right? I'm happy to have a very open discussion about 400 gig, because it is important that, especially for edge purposes, that we all agreed we're doing the same thing, so that no vendor or no go out and do something opposite, right? Like it's like, oh, 8-lane optics, right? It's like, no, we need one decision. And I think there will be a lot more presentation that looks like this from other big companies on kind of how we define what the standard will be. Like, it was like, if you remember back in the days when 100 gig was new, was the same discussion, right? It's like, what will be the future technology? What will we do? Will we do 100 gig LR4, or will we do, was discussions about 100 gig FR4 as well back in the days, so CWDM4, if someone remembers that, as edge peering. So this discussion needs to happen now, and needs to happen in parallel on many places at the same time. Okay, cool. So let's speak about 10 gig and 100 gig. So this is where it's starting to get like, what's called, offensive, which is great. So 10 gig will basically not be offered anymore. Like, that is something that we must kill it. And I will explain to you why. So today, everything we do, all the new boxes we buy is these pizza boxes. They all look the same. They have 32 by 400 gig ports. So if we want to produce a 10 gig port, we must sacrifice a whole 400 gig port for one 10 gig. Like, that is the reality, right? Because you can do breakouts, right? There is these 40 by 10 gig QSFP breakouts. And we can use those. That is okay. But we can't use the same optic for multiple ISPs, right? Like, if you have 10 gig, you have ISP 1, 2, 3, and 4. Like, we can't put it on the same optic, because if one ISP have problems, we need to take 3 other links down, right? So if you work for ISP number 1, and we need to troubleshoot ISP number 2, like, you would not be very happy if we had to take the whole optic out. Like, I'm okay in terms of like striping ports over a large fabric for the same ISP. Like, if you're ISP 1 and you have 40 gig, you can have them on the same optic. I'm okay with kind of that redundancy model. But if you're other ISPs, I'm not cool with that, right? Like, we have never supported it, not even back in the days when we had 10 gig native networks and we had like 1 gig breakouts, right? Like if you're different ISPs, you get an optic yourself. So that is, 10 gig for us, it is dead technology. Like, we will have the same cost to produce a 400 gig port as we do like two 10 gig ports, pay off to do a 400 gig port within 6 months for us, given the cost of cross connects, right? Like, a cross connect, like here in Scandinavia, it's not that bad, but like if you want to cross connect in Ashburn, Northern Virginia, that's almost $400 a year, per month, very soon. They are like 385, right? So for us, that is basically a 400 gig port per month, right? Like, that is kind of what these 400 gig ports cost. So 10 gig, if you're a 10 gig network, then we will most likely have to send traffic through your upstream, or even an IX, right? Like for once in a lifetime, like, IXs are relevant for those networks, right? Like, we've been trying to move all traffic off of IXs for a long time, just to have planability, scalability, and performance, right? But if you're like a 10 gig style network, then peering with AWS will be hard. 100 gig is fine. No problem with 100 gig. We can do pretty cost-effective breakouts on 100 gig. Either we can do the 100 gig optics, or actually from today we'll start using these 2 by 100 gig breakouts on LR4. So they are actually pretty cool. I'm also happy to take, if anyone is interested in LR1s, that is also basically free technology for us, since we're already buying the 400 gig LR4, which can be broken up into 100 gig LR1s, so 400 gig LR1s. So that is technology that already exists. We have it today. If someone wants to use it, we can do it. Like, it needs to be some kind of scale on it. But if people think that this is a cool technology, I'm happy to take your interest and how we can do about it. Cool. All right. So since it's me, I also have to speak about RPKI, and since Job is not here, which it typically is, it's kind of like on me, I guess, to speak about this. But I will keep it short so you don't get bored, because this is pretty boring. But I wrote a blog post about it last year. I think it was a pretty good blog post, if I said so myself, because I wrote it. But we are dropping RPKI invalids in 100% of our border. It doesn't matter if you're a peer, if you're a customer, if you're transit, whatever you are. Like, everyone has RPKI OV. And we have also signed basically all of our space. Today we have the largest pool of signed IP space in the world, which is pretty cool. And we see a lot of effect of that. We drop a lot of routes, and there's a lot of big ISPs that are stopping hijacks towards us basically every day because we have signed all of our routes. We are a very, very good, like a prime target for hijacks. People love to hijack our stuff for various reasons. So for us, it was a must to kind of go through with this. And I think that everyone that runs an ISP today has to do this. It doesn't matter if you're like Jutland's smallest ISP or if you're TDC. Like this is something that's going to have to happen eventually, because like we have seen the effect of some of these hijacks, you know, where we can lose millions in a day, right? Like while that is maybe not true for an ISP, like it can hurt real bad, right? So I think the investment now is so small, it's so easy to do this. Like all the software are there. We are using standard off-the-shelf software to kind of build all of this technology. And it works for us. So we're the largest company in the world, right? So, and we have one of the largest networks in the world. It works for us, which means it also works for everyone else, like with just a little bit of time and effort to do it. So kind of how we implement this, so we have something that we call an IP vending machine internally. Like we have hundreds of teams internally. They build services. There's like Kubernetes people and like Linux people, Microsoft people, other people, blockchain people, storage people, database people, all kind of people, right? So they are all like self-organized teams. They're trying to do whatever they do. And all of them need IP addresses, right? So we have one vending machine that serves everyone. And when you go and put like $1 in the vending machine, or rather nowadays it's like $25,000 to buy IP addresses internally, it is what you get is you get the amount of IP addresses you need, and you get ROAS, and you get IRR updated records that it's keep up to date automatically, right? And that was the only way we could see that this actually works. And a pretty popular service we have, which is getting popular each day as well, is bring your own IP. Great for big enterprises, like old enterprises that has a gazillion IP addresses that they don't know what to do with them, and they don't want to sell them because they were not in the books in the first place. So it's like for some companies it's really hard to sell IP addresses because then they are visible, right? So what they do is that they bring it to the cloud, and we take care of them for them, right? So we take care of ROA renewals, and we help them with IRR updates records as well. So today, that's been a big discussion, right? With like people that have legacy objects. Like we do not support that because we do not skimp on this policy, right? It's like if you want to bring your own IP, it needs ROAS, it needs IRR records, and it needs to be correct because otherwise we can't verify anything. So that's been a big pain pressure for some governmental customers that wanted to move on, but they just had to accept the fact that they had to go to RIPE or ARIN or whoever it is, register their objects and put it in the books. And we're more than happy to serve it from the cloud, which I think is pretty cool. And also everything on our RPKI internally, it is handled by the NOC as a severity 1 service. It is the same, like if RPKI goes down for us, it is the same kind of severity if like, I don't know, DNS goes down or DHCP goes down. Like for us, it's a tier 1, severity 1 service, which I also think is very important to kind of treat it as such, and not like some weird thing that the network engineers does on their free time, right? Like this is real business. Okay, so where are we going? So we are already doing it. So we're moving into delegated RPKI, which means that we run the CA ourselves, both because we believe that we are better at running infrastructure than some of the RARs. We also believe that we can kind of offload them a little bit. I think we have broken ARIN about 4 times already when we publish ROAS. Like they have like 2 servers in Ashburn. That's kind of ARIN. That's like ARIN for you, right? Like we have a gazillion servers in every part of the world. So maybe we should use them for something, right? So that is something we're doing. We're already doing it in South America. It is really the only way to do it in South America. So we kind of started with that. Next up is Africa. So for Afrinic, we believe that we absolutely want to run things ourselves. And after that is done, time for rest of the world. Then we are going to bring, like 3% of the global IPv4 space into our own delegated RPKI solution. The BYOC process sucks today, or it doesn't suck, but it is super weird. Because we need to put X509 certs in people's RAR records. It looks super weird. People always find them occasionally, and it's like, put it on mailing list, and it's like, why is there an X509 cert in this IRR record? And it's like, oh, but that is the AWS process, and then everyone forgets to take it away. It looks a bit stupid, but why we do it is that while RPKI and ROAS decides, it's like, hey, this prefix can be announced by AWS, but we need another step internally. It's like, but which customer is it? Like, how do we know which account we're going to tie this into? So that's why we have another like RPKI-like process with these makeshift X509 certs. So if you ever follow like CyberOps on IETF, I'm very involved in that together with Joe Snyder's. We have the RSC standards, which is basically sign whatever with RPKI. And this whole whatever for us is customer accounts, so that we know with a sign authority who owns which IP address. Like, we are cool with understanding like this prefix can be announced by AWS, but which customer is it internally? So that's why we like, for example, and I'm officially supporting like RSC, for example. So as soon as that goes into and becomes an actual RFC, we will probably be the first user of that, that to be RFC. So work with the reach out to networks. It's still here on the slide. It's actually like a year old slide. We will stop doing this. Like we did it a little bit in the beginning. We have Victor over there in the corner. He had to reach out to a lot of networks. He's like, hey, please fix your invalids, right? And we did that. A couple of them fixed it. A couple of them didn't. So it is like, if you still have invalids in your network, like, sorry for you. Like we're going to drop them. Like we will not route them. And if that's a problem, it's on you. And it was, a challenge in some countries like India, for example, right? Like, they have a lot of invalids, and they're probably still the #1 originator of invalid prefixes. And they simply can't reach us today. And that's, like, they need to fix their stuff, because we will not do any exceptions. And so far, we have built an exception mechanism in our network, but we have not used it once. We will also continue to work on like manners and these kind of things. I'm part of the Manners Cloud CDN working group. I still think there is some things that needs to be done through natural organs such as that. But we'll see what that will be. And also, still help RIRs to improve stability. A couple of them that comes to mind is like Taiwanic, Indianic, Indonesianic. They are not really fit. Maybe they're fit, but they don't have at least the technical infrastructure to support a global authentication system. So we believe that they need some help, either financially or by, I don't know, free VMs maybe, to make sure we have like a globally stable system. Okay, cool. Last slide. So if you want to talk with us, like, you can always talk to me. I'm responsible for all of Nordics, Baltic states, Russia, Ukraine, United Kingdom, Ireland. So like basically every country with snow is my country. So if you operate infrastructure in any of these countries, please talk with me. For like general things, we have the general peering alley. Like peering, like there's always this, oh, Amazon doesn't answer on peering emails. And it's like, that is true, depending on who you are, right? Because it is important to understand that we are not an open peering network. Like, we do not peer with everyone. We peer with people that make a lot of sense to us. Since we also do offer like DX, like some customers are perfect DX customers, right? And some are perfect peers. And we have a process to determine that. Like, most companies are perfect peers for us. We're happy to pair with them. We're happy to build out. We're happy to support whatever they need to do. And some are very good DX customers, I would say. So the peering mailbox is basically dead. That inbox sometimes gets 1,000 emails a day of like status, maintenance, blah, blah, blah. So it is spammed to death, I would say. So that's why we have regional aliases. So if you email that -EMEA, that will absolutely get an answer. For technical things, we have peering-TO, so that's for technical operations. So for any that type of things, happy to take things from that. Peering-DB is our source of truth. So that is where we keep all of our records up to date. So that's where you go and find where we are. And yeah, IRC is still okay. I'm Hugge on IRC. You can find me anywhere. And we have a couple of others from our team too that answers frequently on IRC. So that is everything for me. And I'm sure there's a question from Fergus.
My question is, does anyone have any questions? Because I've already asked him my difficult question last week.
Yeah.
No question. Oh, thank you.
Oh, Clay. Oh, yeah. Let's go, dude.
Head to head. Here we go. Wait for the microphone, please. We've got people watching.
I think it's going to be really... Oh, Clay Haynes, Twitter. I think this is going to be a really simple question. Just notice on your slides, some of the contact information also included FK back at Amazon.com for everything else. But
Yeah.
what about the Prime shipments?
So that's why, oh, sorry.
I know
Right.
it says accept that, but where should we send our queries for Prime
Yeah, so
shipments?
there's anything, if you like bought like a USB memory or something of Amazon.com and didn't get it, like I'm not the contact person for that. Like if your package was broken when it arrived, I'm not the guy either. Like if you did get a like bad banana at Whole Foods, not, like I can't help you.
That's fair. Although when you say RC is still cool too, what channel, what...
Yeah, so obviously DKNOG, I'm on a DKNOG channel, of course. There is a couple of other pretty cool networking channels as well, like #IX. I guess it's a very common way to find us in other big networks too. And Dash Networker as well on IRCnet. Right. Or if you like to practice your Swedish, we have #ISP on Irknet, right? I'm sure that Mattias Sandberg over there likes to talk to you about behaving on IRCnet, right? So,
thanks a million.
Thanks.
Any more questions? Oh.
Tom Klaffler, do you currently, as of today, have any LR1, 100 gig LR1 in production? Or is this entirely pipe dream, maybe in 6 months, a year, whatever?
So for external purposes, no. For internally, yes. So we are a big user of it internally. That is why I said it's like free technology for us, since we don't need to verify a new technology. Like because everything we do is certified, blah, 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 internally according to some very internally expensive processes, right? So LR1 is already done for us, which is like, hey, we can do this for free in the edge, right? Like I can use that technology. But edge, no, not a single port active today. But if anyone believes in it, I'm happy to kind of look at options for it, because that would save us and probably you a lot of money. Yeah.
Any more questions? If I walk away, is someone here going to? Last call.
Right.
Thanks. So next up, we have Rory. Oh. Rory's going to talk to us about repairing networks at scale.
Thank you very much.
And he's going to have slides.
I hope.
Again.
All right. Hi. Welcome. It's lovely to be back at DKNOG. I'm glad you all accepted me back this time around again after last time. If you don't know me, I'm Rory. I work for Google. I'm a recent SRE, ex-network engineer, and I want to talk to you today about how we do repairs at scale as an SRE approach. So, what is a repair for us? Maybe smoke starts coming out of a router, goes on fire a little bit, vendor says thermal event. Sadly for us, that's a repair. Now, there's many driving factors for repairs. Obviously, the biggest one is growth. We have customers that demand smaller failure domains. That means more devices, more of them, more complexity, more prone to failure. Organic growth. Routers are getting cheaper, thankfully. And hardware is getting a lot more complex, like really complex, as we saw in the last few slides about even the complexity of optics is getting exceptional. So this obviously drives a lot of repair. This causes problems at scale. So I want to talk to you about some of the maybe wrong ways to do, or not great ones, to scale out your repair process. As we all know, hiring more network engineers is not a good answer to a manual process. They're a finite resource. There's not a marketplace where you can easily go get network engineers. There's not thousands, there's not tens of thousands. It's extremely scarce resource. And as we've noticed, roughly post-pandemic, hiring is another challenge that I won't talk about. Another non-answer would be buying routers that don't break. We have some fantastic vendors here that would like to tell you that their stuff never breaks and it's bulletproof. I wish that was the case. Things break. Another approach make your engineers work faster. Might scale for a few weeks, months maybe, and then you have a different type of hiring problem. So non-answer. Another approach to not having to repair ever again is build an extremely complex network that is so big you don't need to repair. Sadly, you'll get to a point eventually where a device breaks, causes an outage, you actually need to repair. So absolute non-answer. So how do we move from, should we say, a bit more of a manual process towards something that is a bit more scalable, easier on the engineers, predictable? It's really about repair to engineer ratio. And you can see, mostly we all start off with networks around the 1-to-1. One repair, one engineer. It's a human-centric process. Something breaks, on the phone to your local TAC, you take out your IE cert, you dust it off, you try to remember the command line skills, you prod the command or the router a few times, you talk to the vendor, there's back and forth. It's one-off, it's ad hoc, it's an art, it's a skill, but it's not predictable. And it's really network engineering centric. And that is fine, but when you start to get more repairs stacked up to the individual engineer, you start to see a behavioral pattern where engineers absolutely love to optimize process and automate where possible. So you start to see tools emerge. Maybe it's just a one-shot tool that goes, line card went on fire, drain traffic, offline it. Maybe it's something as simple as drain an entire router, offline it, gather some debugs. You start to see small atomic operations emerge in code. And then you start to see patterns emerge in those tools where you have a kind of an informal workflow emerging based on the tools. And the engineers themselves start to chain them together. So you orchestrate tools, and then you start to deal with escalations a bit more. And it's great, but where we want to be in general is no humans involved for the physical work. We want to have a predictable, reliable system, and that sadly means removing humans where we can. For that, we start with APIs toward the vendors, so that, not just open a new case, but a dynamic two-way system where vendors can come back to us as well. That'll handle like all the data collection, move up to the vendors' cases and keep everything in sync and updated and nice. Internally as well, we'll need to have APIs towards partner teams like logistics, on-site, people who will coordinate RMAs and do the physical work. And where we want to be is our engineers shouldn't be handling the repairs. We should be thinking about code changes, like diffs approvals, and not the actual repair itself. So quickly, lifecycle of a repair. You get an issue. It might come in via IRC, an angry phone call, alerting system. There's a detection somehow. Once you get a detection, move towards mitigation where possible. And then you can start to figure out what actually went on fire, what broke. So you have the local troubleshooting that I was alluding to recently, where you back and forth with the vendor. There's some level of data collection at the start internally to figure out something went on fire, we should probably do something. Then you get involved with the vendor. There's a back and forth. Maybe we find a broken part. And in this case, a part could be a piece of software, line card, router, optic, whatever. We agree on a process to get the part replaced. So RMA with the identifying information, like when is it going to arrive? What shipment is going to come in on? What's the serial number of the new part? Then we go scheduling, fix, like get it actually replaced, get somebody physically in there, get the device. Then we go to verification, like did it fix the problem? Are we good? Can we close? If we fail verification, obviously we've got to go back to step 2 and hopefully not get caught in an infinite loop, but you know yourself. If we pass verification, we're good to close. Repair is over. Everyone happy, I hope. So I want to talk a little bit about API towards router and what would be a good API. So we obviously have to collect diagnostic information. And like when we get the initial alert ingress, at that point we will grab data, some standard amount, like maybe it's a show tech on one vendor or an RSI on another vendor, but some level of diagnostic could also be a trend line over time of DBM on the interface, CRCs, just something. We'll grab inventory data, so what's in the chassis, what's its, or pizza box, what's its current state. We'll want to be able to online, offline components and understand the status of the component as it comes along. Now, while we've had a great presentations, especially yesterday morning around automation, sadly, CLI is not a great API. Neither is SSH. And I can't believe I'm saying this in 2022, but SNMP is not bad. I'm saying it now, so you can't throw tomatoes at me at the social yesterday. So it's not awful. It does the job. It's structured text, and that stands for something. Better again would be netconf, some level of XML over HTTP like Juniper does, like a structured text that I can verify and parse, and I don't need to worry about it too much. So these would be desirable behaviors for us on the back end of the API. And then we'll talk a little bit about the API towards the vendor. This is where it gets a bit more interesting for now. So obviously we want to open and close cases, and I think all the major vendors right now, they should have some level of like RESTful endpoint that you can open a case, pull your full case notes down, get full text email updates, whatever. We'll want to also upload diagnostic info, like attach files, and follow up with requests in a structured way. And this one is a bit important because with the initial kind of early days back and forth, one-to-one person where you're on the phone with the vendor, you can have very asynchronous requests in a case like that you need to go ask another human and you need to figure out scheduling. There's no structure to keep track of like a checklist of vendors asked me to do 5 things, I've done 4. Another team is trying to do the 5th one and I forgot because I'm busy. So we want to have those requests coming from the vendor in like structured, identifiable, predictable way. And of course, we want some level of RMA info. We want to be able to track the logistics of a incoming part if an RMA has been opened and maybe return part not like fixed. So we want to be able to track the full life cycle of the RMA. So these things would constitute a pretty safe starting point for a vendor or an API towards a vendor for us. And the life cycle of the vendor tag. Historically, like I was saying, pick up the phone, my stuff is broken, help. It's very human-centric. It is an art. Where we're going to right now is we have some level of RESTful interaction with vendor cases. We can upload data via the API, but that's not what we want. We want something a bit more structured. So we want the API for the vendor to come back to us as well. So we want them to be able to issue commands towards us without a human involved. Just, I want some show command from this device, and they get it without a human. Maybe they want to pull some log files from the device. We don't want people involved in this process. We want the vendor to be able to like press button, get logs. No delay, just fast, easy, predictable. We want the vendor to lifecycle manage the RMA, as in they will issue it. It will trickle a bunch of workflows internally for us, and they will get the notification, part swapped, replacement part inbound. And that should be it. Like they shouldn't have to think or worry about our logistics in general. So this is where we'd love to go. And I know it's aspirational, which brings me to how. Vendor tag is very one-sided. Like I was saying, the engineers involved in the tag cases on the vendor side, they can't trickle or call APIs on our side. So we created our own. We asked the vendor to use it. So as you can see, we allow them to request commands. They get structured text back from us. Same with RMAs. It all just end to end, it's great. Benefits, obviously, it's amazing. There's low predictability or very good predictability on processing of requests. There's no delay. Maybe our engineers on our side are on holidays. It's no longer, it's fine. It's all driven by the vendor support who can get the data they want in a timely and respectful amount of time. We can also look at our history of repairs. Like, are we repairing too much in one site? Maybe we should investigate something here. A certain class of hardware, maybe there's something wrong. Maybe one vendor is a bit more difficult than others. We have good historic data we can look, analyze, and think about long term. And we can also validate requests, so we can create like whitelists. So maybe we'll deny certain requests, like impactful ones, reloading line cards, issuing odd commands that write to unknown parts of the ASIC and the line card, stuff they might not want to do, tricky stuff. So this is great. So quickly, life of a repair for us. Like I was saying, you get alert somehow. Something in your network went boom. That will generate an alert. You might have internal, could be coming from anywhere. For our current system, what we do today is we will issue directly a level of like a collection of data depending on the type of component that has failed. So we will gather, like Showtech by default, we'll gather logs. If it's optics, we'll gather diagnostic data like DBM, interface errors. We'll log when it happened, when it was detected. We'll restart the component once we've enough data to like start the initial debugging where we have a broken state. We'll automatically mitigate shift traffic, reload a component, wait for it to come back up, see if the alert is cleared. And if it doesn't, we gather more data at this point, post-reload, open a vendor tag case, get all the diagnostic data, dump it into the first case notes. This way, packager gets a case, it's well-formed, there's enough data to start debugging. No SRE, no NetEng, nobody, Google is involved on this part so far. It's all automatic, it all happens very fast. Then there's the back and forth. Vendor might request more, might issue an RMA directly. But if the vendor needs more data from us, it doesn't come to us. Like, it doesn't come to a human, it comes via API that we ask them to use. So they get their data as they need. RMA is approved, might not be an RMA, it might be a software fix, but same thing. Part is shipped, logistics gets involved, repair is done. On-site person gets a pretty good self-guided UI, so you don't need to be an expert. You don't need to spend the time with maybe a network engineer on the console in a video call with your on-site local hands to say, did you insert the line card correctly? Are the pins broken? You know, I can't see it coming back on again. So this is all simple. You don't need an expert locally to replace parts. You don't need to burn another engineer elsewhere. Verification kicks off, audit kicks off, and hopefully we're golden. Quickly, an overview of how we put it together. This is a good reference slide to see how it all fits together for us. You can see, like with telemetry, you know, we'll pull data, we'll figure out something busted, and alerting system will tell us, and then the decision will be made. Everything happens automatically. Which is great, which brings me to a good and simple conclusion that our philosophy is always going to be cattle, not pets. It's a core ideal of the SRE world. We don't want to spend a lot of time on one-off processes that are art. We want to gather enough data to classify problems and take care of those. Mitigate entire classes of problem, iterate on that ideal, have it fully automated, and scale that way. We start with an API, and like I was saying, CLI, sadly not API, but we should start with a API which doesn't involve humans and try to mitigate or bind these together with systems to make it all scalable. Ultimate goal being fully automated repair. We want you to think about playbooks and processes because those are easy to translate into code because we want you to write code to repair at scale. And with that, I want to say thank you for your time and hopefully open the floor to questions.
Thank you, Rory. Oh, choices. 2 questions at the same time.
Thank you for this insight. My name is Lasse Ligard from Kindrel. So this really looks fantastic. Stuff breaks once in a while. Sometimes APIs change. You don't necessarily get a notification about that before it happens. Do you have anything to monitor the automatic execution of this process?
We do.
Setup. And the second part, do you have any triggers or monitoring of the general process and execution of it? And can someone step in and take control or drive it or interrupt it somehow?
I'm glad you asked me 2 questions because I have one answer for you. Yes. If a vendor asks for a command that we have not seen before or might consider it unsafe, then it will go to an SRE and we will evaluate the request. So, and that is with multiple other, like if there's a failure in the workflow, maybe we have recently upgraded some version of software and a component of that breaks, like maybe getting a show tech from the device breaks. That will trigger some level of failure in the code, the system, and that will fire an alert to an SRE. The SRE will then debug and send a code fix to the system. And that will ultimately bubble outwards to production and hopefully the problem is solved. But again, as the SRE approach, we think about working on systems and that will include strong monitoring for the system itself. So if it throws an error, any kind of exception, which was like, we can't get this from the device, then that bubbles backwards to an SRE. So the loop would be closed that way. Does it address all? Yeah, perfect. And of course, systems fail, but ultimately it'll go to a human to evaluate. Any other questions?
Hey, Rory, thanks for that presentation. Tom from Cloudflare. You're mostly talking about, or from my perception, talking about hardware failures where you need to go back to a vendor. Given you run a massive network at scale, I can imagine that a lot of the issues that you run into on a day-to-day basis are also related to peering partners or transit vendors or anything related cross-connect-wise. Is there any plans on augmenting the existing system to have similar APIs for peering partners through, for example, the ISP portal?
Another simple answer for you, Tom? No. That's a different system. But we can have a chat offline because that's about a different set of systems behind isp.google.com, which should be your one-stop shop as operators and like ISPs for your interaction for like opening tickets with our knock, provisioning new ports, bringing up peering, and that would be that system. This one's slightly different, but answer your question? Okay.
Yep, thank you.
Any more questions? Oh, which is the quickest way to get there?
Hello, Matthias from Cisco Systems. You mentioned when it came to network monitoring and managing protocols, both SNMP, which, I mean, I don't think I share your enthusiasm, and yeah, I mean, I was curious, what about GNMI? Have you gone away from using that yourself, or is it just for the applications you're interested in, the hardware support isn't there, or did I just miss that slide?
No, you're correct. It was subtle. So yes, we use all of them. Okay. It is, again, I don't mean to give like a simplification. It's just with a rather large network that has grown over time with multiple vendors and iterations and approaches, we use everything. We would hope to not have to use screen scraping, SNMP, etc., etc., etc. As some of you probably know, some of the older optical gear is ask me about TL1 over a beer. But yeah, to answer your question, device telemetry is all of it, and sometimes in parallel.
Any more questions? Great. Well, thank you very much, Rory.
Before I go, 2 more things. Oh wait, wrong way. First is, if any of this is interested, we are hiring, so have a chat. And I'm surprised for the audience and what we talked about earlier, nobody asked me about free and open source solutions to this, which is why I had a bonus slide. There are components to build these systems already in the world. Like, there's a bunch of wonderful tools that you can use today to get a programmatic API to your devices. To repeat what I just said, CLI not an API, but sadly sometimes you have to use what you have. But there are other better options. Like I said, SNMP, RESTconf, DEFCONF, GNMI. There are options so you can start to build your processes better. There, sadly, is text parsing. There's Python and Go, which right now are available, easy to use, good to learn. They have libraries that will allow you to build an absolute abstraction to your vendors. So you can just go, here's my interface to Cisco, maybe XOR. Here's my interface to Juniper MX. Wrap it all up in ABC, and you have an abstraction, and it is wonderfully easy to use. So don't feel that there's a barrier to entry here. You can approach these things today, all of you, and I hope you do. So thank you.
Thank you again, Rory.
And thank you very much.
So, our final closing act, all the way from Stockholm, Sweden. Patrick Fallström.
Thank you very much. Yes, NetNode in Stockholm, but I actually live just over the bridge. I drove an hour this morning. There's a little bit of cheating. But anyways, I understand that you had a good evening yesterday. That's interesting. Huh. Okay, generating PDFs is kind of sort of something that doesn't work sometimes. Anyways, Patrick Fallström, I'm Technical Director and Head of Security at NetNode, and going to talk with you a little bit about the difference between redundancy and diversity. Because this is something that comes really, really close to our heart. Because when you want to, this just doesn't work. Should we do something else? Who has the computer? I can send a link to Google Drive or something. Who is running the computer? Or I'll just talk anyways. This just takes time. Okay, we get it. Anyways. So a lot of people talk about redundancy, and redundancy can solve a lot of problems by having multiple entries, multiple boxes, multiple anything. But sometimes these redundant entities actually are dependent on some kind of single point of failure. They're connected to each other. They have the same control plane. They might have sort of the same kind of fiber, maybe the same vendor, maybe the same whatever, same something. And that is something that you have to take into account when you're doing your risk analysis and when you look at what kind of threats you're nervous about. So on the scale between something that is completely redundant or what I would call diverse, that means that you have absolutely nothing that is in common between multiple entities. So from the complete independent entities to something that is just in one box, if you understand, is a grayscale. And this is where you can sort of debate what redundancy and what diversity do you really need. And that, of course, depends on what your threats are. You might, for example, like to some degree, as you will see in my example, when I will talk about how we at NetNode are producing time and frequency at the various diverse nodes, as I call it. But on the other hand, we use a lot of equipment from the same vendor at those locations. And that is a calculation of risk that we have taken, and I will explain a little bit more about that. So when talking about redundancy, sorry, let me take a step back. If people just talk about redundancy, to me that is not really enough because as not until people use the word diversity, that is the time when I understand that people are starting to think about how much diversity do you really need. So geographical diversity is of course something that is quite good. It might be the case that you have flooding, you might have fires like we had in Germany the other year. It might also be the case that, as in France, Free released these pictures. A lot of people that I've been discussing this with have said it's a little bit weird. They talk about the fiber being cut, but you cannot really see any fiber here. There are some other pictures where you actually do see some fibers, but you have these kind of cuts that happens now and then. No one really knows what actually happened. You might have fires, you might have other kind of natural catastrophes that impacts some of your physical infrastructure. So geographical diversity is of course one thing that is pretty good, but then you might want to have diversity in other layers in the value chain as well. So this is neither Swedish nor Danish. I think these slides have a hangover.
Patrick,
anyways,
we've uploaded the slides to the website, so you can follow along on your laptop if you have one.
We do it that way instead.
Can you? So for people following along, you can read the slides on the program agenda and not rely on the screen here.
This is interesting. What do you have an... Okay. Are you opening other slides, or should I give you an HDMI connection? Okay. There. Thank you, Philip. So the important thing is to do calculations what kind of risk you have. What kind of risk do you accept? What is your risk appetite? What kind of threat do you see? What is the most risky business? So geographical diversity. Oh, this works. So you have the fiber. Thank you very much. There were some problems with embedding the fonts in the PDF, I understand. So anyways, so we had the fire down in OVH, where some customers actually had multiple racks in different locations, but in the same building, and the fire was big enough so that actually bad things happened. Of course, just because sometimes everything just goes bad, like at OVH. Maybe it was a risk that was acceptable. That is also something to remember, that when you have someone that has some downtime time, it might be the case that the risk they calculated gave them the result, ended up in the result that they saw that risk is acceptable. And instead, it is a risk that is known, and if you have a known risk, then you probably also have a process for how to do restoration. So risk appetite means that you probably have a known risk that you're able to handle if it is the case that you have a crash or if something happens. So if we look at sites, which is what we do at NetNode, we have a site here in Copenhagen. We think it's really important that our sites are diverse, so that the sites actually are independent of each other. Where also the services at the various sites that we have are diverse. But of course, we have made some choices of having some similar components of the various sites, like the way we build the control plane. We need to be able to, like you saw in the previous presentation, we need to be able to understand what's happening. There are some single points of failure there. It's also the case that we use a similar hardware, as you will see when we talk about time and frequency. There is also risks we take, but we have also tried to mitigate that. So the way we look at things at NetNode is that we have diverse nodes. And these are the diverse nodes we have in Stockholm, Gothenburg, Copenhagen, Malmö, Oslo, Helsinki, Sundsvall, Gävle, and Luleå. Each one of these are independent of each other. You might think that, well, wait a second, but you at NetNode, you sell various services where we can connect at one of these nodes and then connect to another one. So obviously they are connected to each other. Yes, but that is as an additional service with transmission that you can get from us independent from how we build the nodes. But the site in Copenhagen, Malmö, obviously consists of multiple locations which are connected to each other. Yes, but we call that all of them being part of a node. So the various locations where you can connect, yes, they are to some degree diverse, but they are absolutely not as diverse as the various locations we have, for example, Stockholm and Copenhagen, Malmö. So Copenhagen, to some degree, the sites in Copenhagen are sort of separated from the ones in Malmö, but they're connected to each other in a completely different way from, for example, Malmö and Stockholm. So we have, at the moment, we have 10 locations in Stockholm, 2 in Gothenburg, 4 in Copenhagen, Malmö, 4 in Oslo, 3 in Helsinki, 3 in Sundsvall, Gävle, and 1 in Luleå. So these are sort of 2 layers of diversity that we have implemented in our network. So, and then for each service that we are locating at each one of these nodes, we also sort of do a risk analysis. And how have we done? And the question now is how we're done with time and frequency. Time and frequency we have at 2 locations in Stockholm, Gothenburg, Malmö, Sundsvall, and Luleå. And each one of them are completely independent of each other. And this is one of the reasons why we do not have an UTC NetNode timescale. We do have a timescale at each one of these nodes. And we are steering that timescale towards the Swedish UTC SP. And one thing that we're working on is to calculate an average of these and steer towards our own average and then steer that towards UTC. But at the moment, we have one timescale at each one of these nodes. And let me talk about how that works. This is one way of being independent. So to be able to explain that, I need to explain first what is a clock and what is frequency. Okay. Some people are laughing. I was laughing as well when I was thinking what a clock was until I started to understand what a clock was. And then I never came back. A clock consists of 2 things. Something that ticks and something that counts the ticks. Okay? 2 completely different things. When you think about it that way, it's not so hard to think about counting the ticks. We just need to agree on what number we should start counting at. That might be hard enough, but let's say that we can agree on that. Let's focus on the actual ticking. When we look at the ticking, we want to have both high precision and high correctness. So we want to be up there. So we need to really know what we are doing. And it's a little bit difficult to be precise because of certain physical problems that we need to accept, like the speed of light and gravity and temperature and other kind of things. But if it is the case that we are going to look at frequency and how things are ticking, the first thing we need to agree on is what is the distance in time between 2 ticks. Okay? This is something that we actually agreed on in 1859, and then we have refined that. So at the moment, a unit of time, which normally is called a second, is a certain number of vibrations of a certain isotope of the cesium atom. That definition is, of course, theoretical to start with, which means that you can never generate that exactly. So you need to sort of adjust a little bit on you. You have something that actually vibrates, and then you need to recalculate and adjust that so you can translate it into the official ticks. So now we have a unit of time that we agreed on. But the next thing you want to know is also when this tick is happening. So when we just look at the frequency and ignore the counting, there are two different problems we have. One is the frequency, and the other one is the phase. So we want the ticks to come at equal distance from each other, and that, otherwise we have a frequency error. And then we also want to have the ticks at the same time, and that's a phase error. Okay, if we now want to have two clocks that actually ticks at the same time, we need to steer the clocks to make sure that the ticks have the same frequency and the same phase. And this is something that is a little bit difficult if the propagation time of the signal, which is speed of light, is longer than the precision we want. For example, we have a clock in Stockholm, we have a clock in Malmö that's like 600, 700 kilometers. It takes, the speed of light is 30 centimeters per nanosecond, and we want our clocks to have a phase error that is less than 10 nanoseconds. 10 nanoseconds is the speed of light of 3 meters. Okay, how do we even measure? From here to that clock is better precision. The three clocks in the back of the room can have the speed of light between them is approximately the error that we have in our clocks between Stockholm and Malmö. So we need to look at the propagation time. And of course, if you know the propagation time, then it's easy to deduct that when we do the measurements. But then because of temperature and other kind of things, you might have variation in propagation time, even in fiber, over long distances. Many of you who work with fibers know that much better than me. And another thing that you might have is asymmetry in the propagation time, that the signal takes, it takes a different amount of time for the signal to go in one direction from the other. And you might think, well, that might be two fibers that are going different paths and whatnot. So why don't you have the signal in the same fiber? But then you actually do have different propagation time in fiber depending on the frequency of the light. So yes, for time, we normally do use bidirectional signals in one single strain of fiber, but that frequency difference that we get is enough that we need to compensate for. But bidirectional signals in a fiber is what we normally use. And then, when we have solved this problem, which by the way, we normally do by we know where our receiver of antenna is in Stockholm, we know where it is in Malmö, we know where the satellites for GPS is, we see a signal that comes from the satellite, it says ping, just like in Monty Python, and then the machine that goes bing, and it ends up at the two receivers, and then we can, because we know where the satellite is, we can calculate that triangle and use what is called common view to do the actual adjustment of phase and frequency. So that's basically how it works. So we do get data from some other clock, and then we have our own frequency source. And this is basically how a clock works. You have a frequency source, you do a phase and frequency adjustment, and that produces your time scale at this very clock. And now in these times when we have a lot of disturbance of GPS, a lot of people say, but wait a second, GPS goes away and then, boy, my car will drive into the ditch or whatever, or my clocks will go wrong and blah, blah, blah. The thing is that if it is the case that your frequency source is stable and doesn't change much, that means that you don't have to get data from other clocks as frequently as if your frequency source is bad. So the more stable your frequency source is, the less often you need data from some other clocks. So if it is the case that you're nervous about getting disturbances or jamming of GPS signal or something because you use GPS receivers, buy a better frequency source. And how good should the frequency source be then? Well, it depends on your appetite on what kind of error of phase error that you can accept ultimately in your application. So what we do is that we use this common view GNSS. We use at the moment GPS, but we are looking at other sources as well, like Galileo. We use cesium frequency source. We do the adjustment, and then we make the time scale at each one of these nodes available with 3 different protocols, NTS, NTP, and PTP. And because these nodes, this is at one node, is independent from each other, this is why the time scale that we get as a result of the phase and frequency adjustment is different at each one of the cities where we do have nodes. And now some of you say, okay, that's cool, but what happens if your frequency source goes poof? Well, because of this, we have redundancy in each one of these nodes. This is not very diverse. There are 2 racks. But on the other hand, we have double equipment of everything. We need to have them close to each other just because of the signal propagation time in the cables. The length of the cables are marked in nanoseconds, so we can adjust. So we buy the cables, send them to a laboratory. We got them measured, we got them back, and we can then adjust the equipment in the propagation delay. So we have 2 different frequency sources that you see at the bottom at each one of the nodes. And then we do have everything else that is doubled. And this is just because we want one node to be as stable as possible. And the double cesium frequency generator we have, what we have seen is that each one of these nodes is stable enough to be within 100 nanoseconds, even if they're isolated in 6 months, the way we have built this. If it was only one rack, it would not be so good, specifically because some hardware go poof now and then. Some power, some PDU or something doesn't want to play. So this is comparison between the Swedish time, UTC-SP, and one of the 2 timescales in Stockholm. And you have the nanosecond. You see that we are within 10 nanoseconds over, this was in March, from 1st of March to 1st of April this year. So after we have produced a time scale, we do measurements with common view again on the difference between the various time scales and the various nodes. So this is sort of evidence that we actually managed to make this as good as the goal is. So back. So anyway, so why talk about this so much? Let's go back. So the goal here was to try to show you the difference between the redundancy that we have within each one of the nodes of the clock. But then each one of these nodes that we have here is completely independent of each other. So on the lower level, we have what I would call redundancy, but on a higher level, we have diversity, even by having different timescales. And of course, some people might say, oh, why don't you have a net node time, as I said earlier? But no, this is actually much, much better that they are independent of each other. So yes, the time in Stockholm might be more different from time in Copenhagen, but that's it. Thank you.
Thank you, Patrick. Good closing act as ever. Any questions?
Everyone wants to go home.
Well, you can't go home because we've still got closing speeches. And there'll be at least 3 hours. Oh, we have a question.
Tom from Cloudflare, thanks for taking the time to answer questions and to do the presentation. With your geographic diversity, is there any plans of having same metro geographic diversity, or is that something that you're not really interested in at this point in time?
Can you repeat that word? If I was thinking in what?
The metropolitan area, so
metropolitan
within
area.
Stockholm or within Gothenburg to have diversity.
Yeah, as you see, we have 2 different nodes in Stockholm which are diverse from each other. That is a request from customers to have 2 nodes in 2 different bunkers which are completely independent of each other. In one of these 2 locations, we actually have a separate node, so there are 2 nodes in one of those locations that you use for testing and upgrades and stuff, just because, as you saw, we have similar equipment from same vendors, so when they're coming with new software, we can sort of load that, and just because we've written our own, we implemented NTS in FPGAs, so we also need to test our own code. But yes, the 2 nodes in Stockholm are completely independent. Regarding Copenhagen, Malmö, yes, there are some interest in Copenhagen in Denmark for us to have a node here as well, and the same thing in Norway, if it is the case. But there are discussions ongoing, and what is also important is, of course, as I just explained, that also the customers of this time understand what they're actually going to use time for, because if it is the case that just like we, just like we use common view as data from other clocks, if our customers in their net node will be up there, right? Which means that also for that kind of more complicated system to get actually some effect, for example, a different node in Copenhagen than Malmö, that implies that the receiver of that service need to understand how to do this. So it lives up to whatever kind of requirements they have. But that is also something that we're working with, for example, the financial and energy sector and stuff to try to do. So yes, we're working on it.
Brilliant, thank you.
Thanks.
Any more questions? If you don't have questions, of course, you can always fill out the surveys, because we've got 3 of them. Yesterday, today, and the whole event.
So when you only
Who are you?
Mikkel from Subspace. Thank you. So when you only have two nodes in a location, do you then use GPS to check if any of them is ticking wrong?
Yes. Okay. Each one of these nodes, each one independently of each other in Stockholm, do have independent satellite receivers that are measured, so we can do this common view measurement. It's also the case that we, from one of the nodes in Stockholm and up to Sundsvall, we're also running White Rabbit, which is sort of P2P equivalent, sort of similar protocol over fiber between Stockholm and Sundsvall that we have done measurements for, but that we also know how to run. But the equipment for White Rabbit is not really stable enough for production anymore. So because you need special amplifiers and splitters and frequency, blah, 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 every 70 kilometers. And the mean time between failure and that equipment is not really up to what you need in a production environment yet. So because we are looking at mechanism of trying to do synchronization without using radio at all. But at the moment, it's not really worth it.
Any more questions? Thank you very much, Patrick.
Oh, thank you.
Just to remind you of us.
Oh.
And next up is Lasse, who's going to give our closing comments, remarks, and everything else.
Yeah, there we go. Thank you, everyone, for coming, and thank you, everyone who was still here, for staying for so late. I know you're eager to go home and have your weekend. I just want to highlight the sponsors that have made this all possible. Of course, NetNode, who have been our sponsors now for 12 years. And of course, Juniper, NetNordic, and Kentic have all contributed greatly. FlexOptic, etc., and Logic and Nokia. Not to the least to mention Norlys, who supplied this morning some hangover restitution for us. That was very much appreciated by some, I could tell. And of course, Arista, Dix, and RIPE NTC. without all of these, this could not happen to a scale that we are today. And of course, thank you to all of you for coming, because you are the primary driver of the event, and we are so happy that we have now 224 people registered for this conference, which is, I think, as Alan said, a record-breaking. So what I would ask of you all to fill out the survey so we can understand how we can make this better next year. And if there anything else you would suggest for DKNOG to do, please contact us, get involved. We always need more people to help organize not only these conferences, but anything else that we would like to organize for the community in general. So with that, I would say do the surveys. We hope that early next week we should have all of the talks available on our website or YouTube. Really, we have someone who will distribute that for us. So thank you, Google, for doing that. You will be able to see this on YouTube, and if there's anything you haven't caught. So with that, I'll send you off and have a nice weekend. And I hope to see you all here next year as well.